Welcome to the Wyoming Department of Environmental Quality, Land Quality Division's Blaster Continuing Education Training. Today is October 6, 2020. My name is Keith Gill. I'm the Public Information Officer for DEQ and today's moderator. Also with me today is Rio Barney, our Land Quality Division Blasting Program Manager. Before we begin, I want to remind all attendees that their microphone is automatically on mute. After each presentation has concluded, we will take questions and comments. To participate, you will need to raise your hand by clicking on the hand icon located on the GoToWebinar menu options. That should be on the right side of your screen. You can also type in your question in the question section of the menu. So without further delay, let's begin. Rio, are you ready?
Yes, I am.
All right.
Okay, can you see my screen, the presentation?
We can.
Yes. Okay. Well, good morning. Welcome to the last of 3 webinars that we've hosted. My name is Rio Barney. I'm glad to have you here. We have about 4 or 5 months ago rolled out a blasting web page. That is the address for the web page. Or you can search Wyoming DEQ blasting. On there, you can find information on the blasting program, the blaster application form, upcoming class schedule, and sign up for training notifications. Today, this is the schedule for today. I will start off with the ISE Level 1 presentation on geology module. That'll be done by Kurt Oakes from Peabody. The next presentation will be a pyrotechnic timing from Brad Brown from down in Nobel. The next presentation will be electronic timing from Ben Sloan, also from down in Nobel. And the last presentation will be blaster personal liability, and that'll be done by Baron Fiedler from down in Nobel. And if you see there, about every 50 minutes or so, I will have around a 10-minute break. This is not an exact schedule, but that's pretty close to what we will follow. Then the conclusion of today's, that'll be 4 hours total. Registering for the webinar just gives you access to the live version. To receive blaster continuing education hours, the affidavit of attendance must be filled out, signed, and returned to me after the conclusion of the webinar. My preference there is through my email address at riobarney@wyo.gov. Here's an example of affidavit of attendance. Multiple blasters can utilize this form. And there, the bottom, there's a lot of blasters outside of Wyoming. If you desire a certification of completion, please indicate here in the last box, and I will send you a certificate for the class. And here's an example of the certificate. At the conclusion of the webinar, I get a report, and that report shows time logged into the webinar, also the interest rating. So basically, if you pull up the webinar and minimize it off the side, that will affect your interest rating. That'll actually show up on a report. Summary blaster continuing education hours. We've hosted 2 webinars so far. They are each 4 hours each, and after today, this will be 4 hours as well for a total of 12 hours. All the webinars are recorded and available on the Wyoming DEQ blasting webpage. And again, the affidavit of attendance needs to be filled out. Just as a reminder here, grace period. We issued a grace period due to the COVID-19 pandemic. And that ends October 31st of 2020. So here in the end of this month. With that though, over the summer, we had to cancel the class scheduled in Salt Lake City. Had to postpone, at least for now, the Rock Springs, Wyoming class. So if you are struggling to get hours, please contact me and we can work with you on an individual basis. I do have several blasters I'm doing this right now with. And then the next class is scheduled for Gillette, Wyoming, November 10th through the 12th. Please let me know if you'd like to attend that class. And there is my contact information. So, all right, with that, I'll hand this over to Kurt Oakes.
Good morning, everybody. My name is Kurt Oakes, and Rio, Keith, thank you for giving me the opportunity to be a part of this third webinar series for the state of Wyoming Blasters Training Hours. Today we're going to talk about the ISEE Level 1 Plus Geology module. What's happening is traditionally the ISEE has always had Level 1 blasters training, which that training is accepted by many states across the United States. Since the publishing of the 18th edition, we have efforted to upgrade this through the ISEE Blasters Training Committee. And that Blasters Training Committee, led by Brian Wingfield and myself as the chairperson that sits on the board, we saw this opportunity as a good opportunity to roll out and introduce some of the Level 1 Plus training modules to our membership across the United States and internationally. So this is by no means a geology course, but it is a basic blasters understanding for basic geologic features, which we all know are a dominant player in blast design. And it's my pleasure to be a part of this class. So, and after this class concludes, and I think there's also an opportunity to chat questions, by all means, feel free to send me a question or send me a question via email. Whatever I can do to help, I'll be glad to help. You'll notice this is the 18th edition with the disclaimer, and there's if you are looking for extensive information on this, you can go to the 18th edition or find other geological references. So on our outline today, we're going to talk, there's going to be a basic introduction to geology, the basic formation and classification of rock types, various features, geotechnical properties, the importance of information on a good drill log. And Jim Knoll, I notice you're on this call, so you can certainly appreciate that one. And then overriding geologic factors of rock. I also want to state that in no means am I a rock licker, but it's imperative that those of us as blasters understand that knowledge of how to read a rock. So you can see in this picture with the drag line at the end of the strip pit, that's out of the old ISEE archives. So like I said earlier, geology is a dominant factor in affecting blast performance. That the type of the rock, the integrity, the competence of it, any bedding unconformities or seams, joint sets, we as blasters need to know how to read that rock. We need to locate those zones. We need to compensate for that in our blast design, not only just how we load it, but also how we time the blast. And we all know, especially in this day and age, we're challenged to reduce costs and utilize just enough energy to break that rock. Not too much, not too little, just the right amount. And if we can understand the geology and the rock type, we can be successful at doing that safely. And it's not one of those things that we can go out and use a cookbook formula, same thing over and over and over and over. We need to assess what each individual pattern is, and through our experience and knowledge, we can evaluate the results we get after each blast. And through that evaluation process, involving everybody on the mine site, the drillers, the blasters, the loader operators, the dragline operators, shovel operators, the neighbors, we can be successful at what we want to achieve. So let's get into basic rock formation and classifications. So when I'm sitting in on one of these sessions and somebody throws up a break page with a picture, I like to try to figure out where that is. So this picture, just to let everybody know, is a dimension stone quarry in the Bloomington, Indiana area, which is that area where back in the day the movie Breaking Away was filmed with all the bike riders. That area is known for its limestone dimension stone quarries. Anyway, there's three different rock types: igneous, metamorphic, and sedimentary. You can see the rock formation cycle starting out as molten magma. As it works its way to the surface, it becomes an igneous extrusive because it cools quickly, and then through the weathering process, breaks down, turns into a sedimentary rock, and then it'll go through various bedding and different rock types are formed from that. And then that zone down there about 7 o'clock, 8 o'clock on the diagram, which is kind of a darker purple color, you'll see the metamorphic rocks. Metamorphic rocks are generally formed from the heat and pressure created around those igneous intrusions, referred to as contact metamorphism. So we'll go through in an order today of sedimentary, igneous, and metamorphic. So a sedimentary rock, and limestones, coal, shales, sandstones, those are the most common sedimentary rocks, but they're formed in one of three processes. They can be deposited, or deposition can take place into horizontal beds. They can also be formed through evaporation. So evaporites include halite, which is also salt. That's what most of us refer to. Trona, down in the south central part of Wyoming. Phosphates that are found out in Utah or over down in Florida. And then coal. We all know that coal is an accumulation of an organic material bedded horizontally through geologic features, which we previously discussed, can be altered and no longer horizontal, but coal is also a sedimentary rock. So when we look at sedimentary rocks, there's various qualities or features of that rock that will affect the blasting of that rock. So if it's a clastic or a conglomerate, so what some of you may be asking, what is a clastic or a conglomerate rock? Okay, those are rocks that are say they started out as a sandstone or a limestone or even an igneous volcanic, and they've broken down for whatever feature. And when they break down, there's a wide range of particle sizes in there, but then there's some fine material that comes back in around those larger particles and bond and cement itself to those larger particles, which create an inconsistent looking grain size for a rock. Oftentimes it'll have a texture of like sandstones, but in my experience, some of the most inconsistent blast results I've ever seen come from conglomerates. Sometimes you can shoot them to bug dust and they're easy to shoot. It all depends upon where these conglomerates are located. Sandstones are also the same type of thing. There's some sandstones out there that are hard as the hubs of hell, as a friend of mine used to say. But others are very soft and friable and easy to break down. It all depends upon the rock type, and understanding that rock type enables us as blasters to produce a safe and productive result. There's shales and mudstones, evaporites like salt, and then coal is considered a biochemical sedimentary rock. So here's probably a better explanation of what a clastic or a conglomerate rock is. But you can see on the picture provided by Ron Elliott of the inconsistent particle sizes in there, along with, you can see the particle sizes there, the coarser particles, and there's a penny, Canadian penny, but it's also surrounded by real fine, smaller, well-cemented particles like a sandstone. And these particles, whether it's in a conglomerate or a clastic or even a sandstone, they're formed through lithofaction, which is that cementing process. And I want everybody to remember that word lithofaction. It's going to come up later in our discussion. So those conglomerates are sedimentary breccia. You can see down here on the bottom right that breccia is more angular, whereas the conglomerates are generally, they have more rounded edges to them. And you can see where, just from the different rock types that are in a conglomerate or a breccia, certain features can come through with those. There's even some gold-bearing conglomerates down in Colorado that can be pretty robust and durable. Sandstone, that's a real common one. If we have any blasters on here from the Midwest, we have our good fair share of hard, competent sandstones, or anybody from the states of Arkansas or Oklahoma, we have some good hard sandstones. Again, they're well cemented, bound together, and the initial formation of sandstones in most all cases is of silica, which sand, quartz, and there's well cemented or poorly cemented sandstones. Mudstones, which include shales, siltstones, mudstones, they're all broken down and formed from clay deposition. And you can see that typically they're very soft and very pliable, and that pliable feature is going to come up later on in this discussion with Poisson's ratio and Young's modulus of elasticity. But the presence of clay is, clay's soft, very fine particles. When it gets wet, it becomes even weaker, and oftentimes it can break down. You'll notice in many limestone outcrops where there is a shale seam, that shale seam will erode faster than the limestone either above or below it. And that can be a route for air blast venting coming out the face and which we as blasters want to minimize those occurrences. Evaporites, salt, gypsum, phosphates. They were deposited in water. That water evaporated out and left a remaining mineral in there, depending upon what that mineral was in the water. There's a lot of in situ salt masses. New York State, just under the city of Detroit, Michigan, there's a big salt mine, believe it or not, under Toronto, Canada, in Ontario, New York State, upper Louisiana, large salt domes, East Texas, and there's some evaporative salt mines over in the central Arizona region as well. And then coal. Most of us on this call there's a good number of coal miners on here, and coal started out as a plant with vegetative matter around it in a swamp. Those plants died, decayed, and then deposition took place on top of it, oftentimes a mudstone or a sandstone, and it just compressed it. So based upon that amount of compression and the type of material it is, when coal has a ranking, and it's ranked into 4 different types. There's peat, which is the lowest and softest, and they still mine some peat in Europe. And then there's lignite, which is above peat, so it's a bit harder, creates more BTUs. The higher the ranking of coal, the more BTUs it produces when it's burnt. And then there's bituminous, which is by far the most common of coal that's mined for use in power. And if it's high enough quality, it's used for metallurgical coal. And then there's anthracite. Anthracite is the hardest, and anthracite is actually considered to be a metamorphic rock because it's formed through extremely high compression rates. And to the best of my knowledge, the only operating anthracite mines in the United States are in northeastern Pennsylvania, around Scranton, Wilkes-Barre, up in that area. So let's get into some igneous rocks. Igneous rocks form when molten or semi-molten material goes through the earth and then cools. And if it cools while it's still in the earth, it's referred to as an igneous intrusive. If it comes out and vents itself into the atmosphere and it cools quickly, it's referred to as igneous extrusive. So different materials crystallize at different temperatures, and based upon what those hot fluids were, dictate the size of the crystals and the type of crystals that are formed. If you're ever around a pegmatite formation, you'll see pegmatites down in the Colorado mountains, you'll see them up in the New England states, in Connecticut, Western North Carolina. The pegmatites, if you're into geology and crystals and different types of unique rocks, you'll be intrigued by pegmatites. So we know that those intrusives cool slower, and then when they cool slower, it gives those crystals a chance to grow and get larger and larger and larger. And then if it's an extrusive, they cool rather quickly, like a basalt. Basalt is an igneous rock that generally it flows out into water. When it flows out into that water, it cools rapidly, very small grain sizes, and highly jointed. So here's some examples of igneous intrusive rocks: granites, gabbros, diabrites. And here's some examples of extrusive rocks. You can see basalts, trap rocks, or volcanic pumice. Basalts and trap rocks, in my eyes, are considered the same thing. Very, very similar in what you need to do when you shoot them. Generally very hard, very dense, high in iron content. You just gotta pound it. So metamorphic rocks. These are interesting rock types, and they can be formed from an igneous rock, sedimentary rock, or it can actually start out as a metamorphic rock and then go through contact metamorphism, further altering its condition. So they're subjected to intense heat, pressure, and fluids that change the texture and composition of the rock itself. So examples include slate. Yep, that old traditional slate pool table, that's built on a metamorphic rock. Schists, gneisses, which are similar to granites, but it's a metamorphosed granite is what a gneiss is. Marble. Has anybody in this class ever been down to the Ewell Marble Quarry in Marble, Colorado, not too far from Glenwood Springs? If you can ever go down there, by all means go. It is a great place to visit. It's amazing to see the quality of that marble deposit, and that's the quarry. And in the day it was underground, and in the day that's where the block for the Tomb of the Unknown Soldier in Washington, D.C. came from. And then also quartzites are also a metamorphic rock. So let's talk about rock mass features. So we're talking about bedding planes, we're talking about faults, we're talking about joint sets, and we're also talking about voids and caverns. You can see in this picture how this is a limestone quarry, and it's in the eastern United States, and you can see how severely dipping those limestone beds are in there. So just because it's a sedimentary rock does not mean it has to be horizontally bedded. And these structures, whether it's a joint, a fault, whatever, are important factors when you're looking at the roof stability in an underground mine, borehole deviation for a drill, the propensity of a rock type to throw fly rock, and if there's a horizontally bedded seam, it's easy to get an air blast event. And many times we all fear mud seams as blasters. Those mud seams are features that need to be detected, and they're generally formed along fault lines or joint sets. So also when you're looking at joint sets, where those joints meet or cross or intersect, that's a predetermined fragmentation plane right there. You as the blaster, when you're designing your blast, you need to get with the driller and yourself, take those into account when you come up with your blast design for your hole diameter, your pattern, hole depth, explosive type, timing. The identification and understanding of what those structures are extremely important. Let's talk about fault lines. So when you look at fault lines or rock deposition, you got two things you need to take into account. You got your strike, which is the bearing of the line of intersection with that rock type and an imaginary horizontal surface. So, and then you have your dip, which is the angle that rock mass is dipping, going down into the earth. you can see where that red horizontal block in the diagram depicts along the line of, which is the longest access of that deposit, that is the strike of the deposit. So, and then the dip is dropping down. So oftentimes strike and dip are noted as, it'll have a strike of, say, north 35 and a dip angle of 20 degrees. That's how it's noted. So when we're talking about these features of strike and dip and faults and joints, you can read a lot from a rock outcrop, and then you can also get a lot of interpretation through core logs, and then you can also go through and use the various state geological agencies who have spent decades gathering this type of information to determine a lot of the faulting and features and that type of information. And then also throughout the individual history of the mine, if it's commonplace that if a mine has a dominant fault in it, or a series of dominant faults, or a joint set that robs a lot of energy, that mine has a good history of that location in the pit. It's important for us to pay attention to that and pay heed to the people when they talk about things like that. In bedding planes are where different sedimentary rocks, or even they convert from one rock type to another type. And you, like in this rock here, this is out of a coal mine in southern Indiana, and you can see where there's shale and sandstones and mudstones and even a coal seam. So those bedding planes, if they're loose enough, they cause a loss of explosive energy. And then some bedding planes also carry water. So it's important to have the drillers note various changes in that geologic structure within the face that they're drilling, especially if they get into a zone where it's making water. And this also goes back to the point where it's always a good practice for the blaster to go down, take a look at the face before he even starts loading, so he has an idea if there is any water or wet seams that exhibit itself in the face. And these bedding planes are initially formed horizontally, but then, like we said earlier, we saw some of those pictures where through tectonic and seismic interactions, they can be folded up like an accordion. There's a beautiful road cut in eastern Maryland on Interstate 70, where it's right on the border between Maryland and West Virginia. It is the best example of an anticline in a road cut that I've ever seen. It is absolutely beautiful. But that bedding can be positive for us when we're shooting, because it can create a nice natural floor in the quarry. The drillers can recognize that change in geology. The blasters can recognize that when they shoot it. And in this picture, it's from a quarry in the Kansas City, Missouri area owned by APAC, but most of the quarries in that Kansas City area, they're working after a rock that's referred to as the Winterset limestone. And it just has a floor that is just smooth as a pool table, and you can see that in the picture here. That rock just breaks smoothly to that floor, and you don't have to worry about floor grade in there, that's for sure. Now here's an anticline. The anticline, you can always remember an anticline because it's shaped like an A or the gateway arch. And then a syncline is the U. That's the low side. And when you get into Appalachia or some regions in Utah, you'll see some of the folding that takes place with anticlines and synclinal structures. So what you want to do if you have the opportunity when you're in an anticline or a syncline structure and you're needing to shoot it, you want to try to orient your timing front or your rows, either one of those. You want to try to get those as perpendicular to the strike of that feature as you can. That way you'll be able to maintain a good stable high wall, and you'll generally see better rock breakage from that. Bed angle and dip. You can see how this is a limestone bed, and there's also, it appears, a little bit of shale in there, but you can see how it's high on the left side of the picture and lower on the right side of the picture. So that's dipping in that direction. And it's important to understand how the rock dips in a particular orientation so that once you understand that, you can minimize your likelihood of having a powder column cut off, or you can minimize your likelihood of leaving high bottom, or you can totally minimize the likelihood of having a misfire, because if, say, the rock is dipping and it's wet in the bottom, that can create enough dynamic pressure that it can potentially cause a detonator to fail or sympathetically detonate. And then also another issue with dipping and jointed rock is excessive back break. So it's important that us as blasters, again, it's important for us as blasters, in order to do our job safely and get good results, is sometimes it's important to turn that face in its optimal direction so that you can time it and take advantage of the rock. Rather than the rock dictate your outcome, you can turn that face and you can dictate to the rock what your outcome's going to be. Faults. So a fault is a fracture in a rock where there's displacement on two sides. And again, that displacement in information for that fault is referred to as a strike and a dip. And in some areas, faulting can be extensive, and then other areas there's not a whole lot. Since I work for Peabody, I have responsibility both in the United States and Australia, and we have two mines in the Bowen Basin of Queensland in Australia. And at one of those mines, our Copabella operation, there was a blast design that I was assisting those guys with not too long ago, where there were 7 different fault types running through one individual cast pattern. That cast pattern was about a half a mile long, but still that many faults of significant displacement. It's a different world over there than what we're accustomed to here, especially in the PRB. Again, each and every shot's different. There's no such thing as a cookbook. So 3 different basic types of faults. A geologic fault, there's a normal fault where the hanging wall goes down. A reverse fault is where the hanging wall moves up. And then there's a strike slip fault where there's very little vertical movement, but the rock mass moves horizontally, more like east or west. So how do you tell the difference between a hanging wall and a footwall? Imagine if you're underground. The footwall would be where your feet are, and the hanging wall is the portion that is above you. So if you're underground in a drift and you're walking down a drift, that footwall is what you're walking on. I hope I'm doing a good job of explaining that. Joint sets. Joint sets are a result of forces, and when those forces oftentimes settling, because you'll see joint sets in sedimentary rock, they're fairly commonplace out in the PRB, and through that settling and equalization of stresses in the rock, it creates planes of weakness, and then those planes of weakness are joints. And generally there's in most locations across the United States and different rock types, there's either two dominant joint planes, majors and minors, and in some areas, especially in sandstones, you'll see three joint set orientations and planes. And then down in the lower right corner of this thing, that's a picture of columnar basalt. So columnar basalt is just loaded with vertical cooling joints in it. And then oftentimes when you're looking at a rock, especially if it's an igneous rock, like what we're seeing in a columnar basalt, or in this picture from Dale Ramsey back in the day, the closeness of that joining will dictate how good our fragmentation is. But one thing you need to take into consideration is when you are shooting a highly jointed rock, if you're in an area near residential structures, take into that account that orientation of those joint sets, if that comes in alignment with any nearby neighbors. Mud seams. These weakened joints or planes of weakness can cause poor fragmentation. We already talked about air overpressure and air blast. Also a potential for fly rock. And then it can also form a plane of failure for a high wall failure, especially if your orientation with the rock mass isn't right. Voids and caverns. If you're in a karst topography, the limestones and dolomites that we have here in the Midwest, especially around the St. Louis area, it's infamous for caves and solution cavities in the rock mass. You drive down any of the interstates in central and eastern Missouri, and you'll see these caves and caverns along the bedding plains. And it's here again, it's the importance of that driller to give you a good drill log so that you as the blaster, as you're taping that hole, as that hole's being loaded, if that powder column rise doesn't continue to rise, you need to take note of that. But that's what a karst geology is. And we talked about this already. Excessive loading of, you can get inadequate confinement, which can cause fumes. You can get inadequate burdens, causing a fly rock or an AOP event. And you can get some really odd seismic vibration characterizations. So let's talk about some geotechnical properties. All rocks have their own density. Density or specific gravity is noted in grams per cc. All rocks have their own unique hardness, their own porosity, which is the amount of void space between particles, their own strengths, which strengths are noted in compressive, tensile, or shear. Oftentimes you can determine what the velocity of that rock is in a P wave or an S wave. And then also its modulus of elasticity is how far will that rock bend before it breaks? And yes, rocks bend before they break. So the best way to measure stress and strain, stress is a unit of force on a given area of rock noted in PSI or pascals. Strain is the amount, it measures the amount of deformation or elongation that that rock can go through. And it can be measured, you can literally take those little wire mesh gauges and glue them to a good clean face and measure what those values are. Doesn't happen too often, but some scientists utilize this information, especially on civil blasting projects. So densities. Densities is a rock's mass per unit volume. And then, so a rock may weigh 2.2 tons per cubic yard or 163 pounds per cubic foot. And then there's the specific gravity of that rock type, which may be 1.28 grams per cc. So each basic rock type has a range of what their densities are and what their hardnesses are. And based upon that information, you can kind of get into a ballpark of what you can expect for a design powder factor, and then it'll also allow you to convert a volume that you're shooting into an approximate number of tons that you're shooting. All the powder companies basically have an app on your iPhone now. And in that app, oftentimes, are a lot of these conversion factors that you can utilize. So, the resilience of the rock. So you can see how that rock in the diagram, you can see how it's moving more up at the top. There's a greater amount of amplitude on the surface than there is in the ground. And on that surface, you can, that's why we, when we can, that's why we measure ground vibrations and seismic numbers on the surface or near the surface of the ground, because it gives us a true reading of what the earth is doing. So that can be broken down into a modulus of elasticity and the Poisson's ratio. So the modulus of elasticity is that ratio of stress to strain. And then that Poisson's ratio is that measurement of lateral strain of like imagine a tearing of the rock. That's what those two features are. And each rock type has its unique modulus of elasticity and Poisson's ratio. Let's talk about porosity. Ron Elliott provided us a beautiful picture of a vesicular basalt. And a vesicular basalt is known for the large pores that it has going through it, like coral in a coral reef in an ocean. That's vesicular. So that vesicular basalt, is it cooled even though it's an igneous extrusive in water? That cooling of gases and cooling of water as it came out went through all those pores. Vesicular basalts are known for, you need a lot of gas energy to get good breakage in a vesicular basalt. Rock strength. You know, you can measure rock. Rock can fail in three ways: either compression, tension, or shear. So we all know that compression is the effect of pushing or hitting something. Tension is literally pulling it apart. And then shear is the process of tearing it apart from one side to the other. In those, the animations on the slide kind of give you an idea of what's going on under those features. So you can see, take a look at this, go down that list of rock types. You can see how strong they are relative to compressive strength. And then take a look at how weak they are under tensile strength. That's the reason why it's important that we all understand the way that we break rock when we blast rock. It's through tension, it's not through compression. Compression is what generates all the fines around the borehole, but tension is truly what breaks the rock and allows that rock to move. And then rock velocities. Marble, which is a metamorphosed limestone, has a high density, and generally the higher the density, the higher the velocity of the rock. Sandstones or shales or mudstones, they're a softer rock, not as dense, so therefore they don't have that similar rock velocity. You can pick up all these numbers through P wave and S wave gathering from seismographs when utilized properly. So the importance of a drill log. This is a drill log that's been used from Al Hooper over in Ohio for years. Al was one of the first ones to adopt a consistent drill log across his contracting business. But you can see how he has rows, how he has number of holes in the row, and then there's a square, and the driller can write notes. And one thing that I always say, when a driller's working with a drill log, if he draws out the pattern, make sure he puts a north arrow on there, and make sure he has a diagram of the free face where that's at relative. That way it allows the blaster to get his orientation proper in case if the blaster and the driller do not have a chance to cross paths and talk with each other. So, and it's important for that driller to provide as much record about how that pattern is drilled. And that relationship builds over time. So let's talk about some overriding geologic factors. So we've talked about cookbook. You can utilize similar blast designs time and time again, but it's important to do your homework before you go down that path. Make sure that all the face conditions are the same. And we all know that geologic conditions can change rapidly. And that failure to locate or identify any of those changing conditions can lead to a fly rock, somebody getting hurt, an air overpressure event, a neighbor complaint, or even poor productivity in the blasting process. So the number one design consideration in all blasting we know is safety. But one of the main drivers to safety is understanding and having the ability to read that rock. So it's important to understand the geologic conditions when you're going in to design a shot. So what we have here is a quiz, and we'll go through this quiz rapidly. Which of the following is not a rock classification? Which of the following is not a rock classification? So if you go back to our presentation, you take a look at that, and you think about igneous, metamorphic, and sedimentary. So that means evaporites are not a rock classification. So what I did, there's a handout that was presented, and it's on the pick list for the menu, and you guys can download that ISEE Level 1 Plus Geology Module quiz, and then at the you can fill that out, and the subsequent page are the answers to the quiz. So that concludes my presentation. Now, I think there's an ability for people to ask questions. Does anybody have a question? Does anybody have a question at all?
The folks here on watching as attendees, you can raise your hand or you can type in a question through the menu options.
Hey Kurt, this is Rio. I have a question for what Peabody shoots. What's the most challenging shooting conditions that you guys shoot in for geology considerations?
Relative to Peabody, I would say by far it's our surface mines in the Bowen Basin of Australia and Queensland. Just the number of faulting and the variation in the rock types which we have over there, as well as the depth of the pits. Those two mines, Copabella and Moorvale, are by far the most challenging. In the United States, you know, geologically, I would say our most challenging operation geologically would be El Segundo down in New Mexico. But when you're looking at the PRB mines, each of our three mines in the PRB, whether it's NARM or Caballo or Rawhide, each of those have unique characteristics with unique challenges. Caballo's infamous for its sandy, wet overburden. NARM is infamous for the tall faces and some of the Ryder coal seams that have a tendency to rob energy. And then Rawhide, it has neighbors and design structures nearby that we have to be very cognizant of when we're designing blasts to minimize the effects that those neighbors and the orientation of the rock drives a lot of that when it comes to blast design and timing sequences. Good question, Rio.
Yeah, thanks, Kurt.
We do have a question from Brad Brown. PRB challenges strong bonding of
overburden to top of coal.
Overburden, yeah, sorry. Hey, Brad, I'm gonna unmute you, and if you'd like to just ask any questions.
I was just throwing in a few more in the PRB and elsewhere here. We get some places where we've got very hard, very solid overburden material right on top of the coal, and if it's strongly bonded, it makes it very difficult to shoot and get the breakage down there without damaging the top of coal. The other part is the big challenge is the lenses, the channels, the rider seams that allow water and even pressure to flow through that affect the blast outcomes. Kurt's well familiar with these.
Yeah, Brad, you bring up a really good feature in topic there on the lenses and ancient stream channels. And it's interesting when you're looking at a rock face and you can see a little U, you know, like the rock's running along nice and horizontal, but then there's that little synclinal feature, which is oftentimes an ancient stream bed. And if the rock in that ancient stream bed, if the deposition is off at an angle, which is referred to as cross bedding and no longer horizontally bedded, those cross bedded ancient stream beds create a form of weakness, and you can get some, like Brad mentioned, a lot of water flowing through there. But the biggest challenge there is the rock stability, the stability of that face in that region, because where those two different bedding planes meet, that creates a weakness. And over time, that'll erode along that contact. So it's important is the blaster when they're going down to take a look at the face before they shoot it, or the drillers when they intersect something like that, they can tell a difference in their penetration rates and how much cuttings are coming up out of the hole when they hit a stream bed. It's important for them to note that on a drill log. Good point, Brad. Thank you.
Do we have any questions, any other questions or comments from the attendees?
All right, this is Rio. Thanks, Kurt. Let's go ahead and take about a 10-minute break. Let's be back in here. It's about 25 minutes past the hour, so Mountain Time 9:25.
Okay, let's go ahead and get started again. Rio, I'm not sure if you have any additional comments you'd like to make at this time.
Just the affidavit of attendance is attached, is a handout for this presentation, so you can also get that there.
Okay, great. Well, let's go ahead and get started with Brad. Brad, I'm going to go ahead and unmute you, and we're going to hand over the controls to you.
Cool beans, ready there. Look at that. Show my screen. That should be showing in a presentation view. I'm going to minimize the bar on the side so that it gives you the whole screen. Does that look okay to you, Keith?
Looks good.
Okay. One thing on the right-hand side, I minimized mine so I can't see it anymore, but there is a handout for some of the timing problems that are in there. You may want that to work it through. You may want to grab it and save it for afterwards to see what it gives. Some of the problems get a little boring when you wait for an answer that isn't going to come. The other thing that's over there, I minimized the chat, so Keith or Rio, yell at me, throw a rubber chicken if you want to interject something at any time, please, and thank you. Kurt, I wanted to thank you for that. That was a great way to tee up the timing side of it. It's critical to know what the driller finds out there, and it's critical to know about the rock to be able to design the blast and pick the appropriate timing. I'm a mining engineer by training. I come out of a Canadian university, so when you hear the oom and boot, you'll know what I'm talking about. Only other thing that's probably important there, mining engineer, that just means too many bumps on the head to work at McDonald's and not enough to be a geologist. So I'm grateful for Kurt doing the talking about the rocks there, and I'll try to latch on to some of his concepts through here when we get into some of the timing bits. Let's see, why do we use delay timing? The obvious thing in there is to break up the shot. You get better control, better blast control when you don't have the whole mast going off at once. For most of you guys, controlling the direction of the movement is critical. You're either pushing it out for a shovel, trying to cast it for a drag line, trying to break it somehow so that you can dig it. I don't care how big your shovel is, you need proper fragmentation and movement, the displacement, to be able to do that. The other part is you got to manage the vibration control. For most of us, even here in the middle of nowhere in Wyoming, we're limited on vibration, and you got to reduce the amount of explosives detonating per delay. Typically, people are still looking at an 8 millisecond delay period, but whatever it is, you're trying to get just the right amount of explosives to break and move it without shaking the fingers and getting it going. And a shout out in advance there, you get past that 8 millisecond limit by getting to electronic initiation, which Vince is going to be talking about. Some of the considerations come in your timing. The geology is huge. It's really a huge part of it. The big part there first is how does the material respond, but then the other parts are where can the energy bleed off to, through the structures, through the joints, channels, whatever it is you've got. For the burden delay, you want adequate time for relief. You want to be able to have the rows move out and give you room for the next row to go off. And the spacing side, the real question is how fast can you initiate the face holds? You don't want to go too fast. We'll see further down here, you get into trouble there. The other thing you've got to do, that geologic conditions, the seamy material, whether it's horizontal strata or the joints and the channels and whatever it is that's vertical or faulting, whatever, it's going to bleed off energy for you. And in some way, shape, or form, that geology is going to dictate whether you shoot faster or slower. Typically, it's going to push you to go faster and faster to avoid getting disruption of adjacent columns. And the other part in there is obviously the vibration control, the number of extra holes per delay or pounds per delay that you can use. A couple of simple concepts there, rock response time and face velocity. Rock response is just how long it takes that first row, if you will, to start to move after the explosives have gone off. If you look at videos, you'll see the shock going, and then there's a delay, and then the face starts to move. You've got to account for that delay in the rock actually moving, because that's going to dictate the fastest that you could shoot an adjacent row, a next row. The other part would be the face velocity, how fast it moves once it actually is going, so that it gets out of the way. typically that's dependent on a bunch of factors, burden, the loading and the spacing and so on. But you also want to, say, hey, do I want it a third of a burden out of the way? Do I need a half? Depends on your application, but you want to see that face moving and getting out of the way, because that'll help dictate how fast you want to do it. Some simple timing rules of thumb: hard to soft materials, granite to cast blasting. You go from short times in granite, typically, to longer and longer, down to much longer times in the cast blasting. That's row to row, okay? And these are not hard set rules. They're just rules of thumb. Spacing delay, 1 to 3 milliseconds per foot down the row. What you want to do for air blast control, though, is avoid shooting down the face faster than the speed of sound. You can reinforce a sound pressure wave, air over pressure wave, and you'll get yourself into trouble there. So 1 to 3 is where it shows here, but you can determine these from it. I guess the other way that you can look at these timing rules of thumb is you can take a look at the guy that's doing the shooting currently and say, you know, do I like the way this looks? Does it give them the muck pile shape, the distribution, the fragmentation, the displacement, whatever it is? Does it give them what they want, or do you look at it and you say, you know, I think I need to do something else? And that's not being hard on somebody. That's taking advantage of your responsibility as the blaster in charge to decide it'd be better to shoot it this way, shoot it that way, change something or don't. Here's something I pinched long ago from John Floyd. This colored chart here at the bottom, there's the title and the gauge for what's going on. Delay intervals in milliseconds per meter of burden. I just haven't rebuilt the thing in imperial units, but he's saying milliseconds per meter of burden. And if you look at the top there in the rock mass, you got a wide range in that gray band for a massive formation. But as soon as it starts to get blocky and jointed and have weak planes, you get down into a much lower, much tighter band in there, where you've got to be careful with your timing. Water-filled holes, very difficult to do. Let's skip on down to the green. If you want a muck pile that's tight together, you're going to be shooting at very tight timing. If you get down a little further and you spread the thing out and really kick it out for a loader as opposed to a shovel, which a loader doesn't have trouble chasing material, then you want to get more and more and way more timing in there. And then the other general things, depending on fragmentation, back break, fly rock, and so forth, you can change things up. Not hard and fast, but some good ranges. Apologize for it being in metric. So let's look at some pyrotechnic products. The title's Pyrotechnic Timing, so what are we talking about? Talking about basic safety first. Don't mix different manufacturers' products. These are all going to tend to be some kind of initiation signal tube or signal system with a bunch of plastic parts connected to it and detonators on the other end. And it's all about connecting this to that, but it's critical that you get the right donors and acceptors put together. That is, you're donating energy from one unit, say from a detonator or a cord, to something else, and it's got to be enough for that acceptor to pick it up and run successfully with it. It's all about, will these things shoot? Will they go together? And will this shoot that? So it's, again, the parts as parts show. Pyrotechnic, I said, okay, that by definition for what I'm going to do is non-electric and not electronic. So that sets us up for detonating cord and shock tube or non-L trademark products. Obviously, I've got a bunch of pictures from the dyno side of the thing, but I've pulled in some other pieces here and there as well. We're not into the mini cords of the old gas systems that they use, or for that matter, safety fuse and starters. We're looking at cord and tube systems. So a quick look at these. Cord, a PETN core, an explosive core with a bunch of textile wrappings and plastic extrusions around it. Whether it's textile and wax or plastic finishes around them, it's just a matter of the type of cord and the application that you've got. The big push on cord, it works well here in the West where we've got wide open spaces, but it's also generically free from hazards of electrical and radio frequency energies anywhere. And a lot of places we're using no in-hole detonators with it. That is, you'll run cord into a booster that is made to accept the signal from the cord, and that'll go off. You don't have a detonator down in the hole that's got timing or something else going on. It's simple. Knotted connections. I used to love doing the circuit calculations, but people got way far away from electric detonators long ago and doing resistance calculations and balancing series and that sort of stuff. Cord, and you'll see with the shock tube systems, are much easier to work with. Cord's really visible, easy to inspect when you're looking at it, and it's from an inventory standpoint, it's beautiful. You got a roll or you don't. Okay. Security's 2 paths of initiation are recommended and very easily achieved. You can box in a pattern and tie across it, and now you've got 2 paths to every hole if you want that. On the disadvantage side, and it's not a knock against it, it just doesn't fit some places. Safety, if you get a cutoff there, you can get things firing out of sequence, which can result obviously in fly rock dilution, fragmentation issues, and a bunch of other things. A downhole cutoff can leave a larger target in the muck pile if your cord is susceptible to initiation by shovel hitting it, digging through the thing, something like that. Some cords can be left in the hole too long and diesel can affect it. It can seep in through. Cord can also be initiated by impact or force. So for example, cord is the last thing you'd use, last thing you'd tie in under a high wall because you don't want a rock falling off and hitting it. You don't want to drive over detonating cord. You don't want to do that to tube systems or anything out there, but especially with something that's susceptible to initiation by impact. And like everything else in the explosives world, can be initiated by lightning strike. It's got an air blast. It's got a great big ball of fire coming off around the thing. So it's got air blast associated with it on surface. Down in the column, it's going to disrupt a portion of the column. So you don't want to use it, say, in less than a 4-inch diameter hole. Some people say 6. It can disrupt the column. It may damage the explosive product down in the column. And for some products, it can side initiate that column. If you go high enough core load, you may deliberately side initiate the thing and get an axial priming situation. So it's got a couple of considerations there to watch for. Most people don't get that far into the weeds, but you got to watch for it. Shock tube, and this is from the non-L side, our trademark stuff. It's out there for its safety. It's when they picked up this, they said, hey, not only do I not have to do electric current calculations, but I'm immune from those stray currents. I can work around power lines, buried cables, shovel power cables, radios, phones, anything like that. This stuff is great. It's strong, it stretches, it shoots through knots, kinks, bends, and it takes a heat and flash simultaneously to ignite. That is, you can't just pick it up and try and burn it and get something going there. It takes a combination of features to get it going. Construction, not a whole lot here, but I left it in for people that haven't seen it. Typically, there are multiple layers, and they have different purposes there. What strength, abrasion resistance, penetration by chemicals and things like that. What really matters is it's a plastic tubing. It's got a dust coating inside the thing. This says 1 pound material, 1 pound of this dust per 100 feet. It's just a very little bit in there, and what you get is a dust explosion running down this tube at about 6,500 feet per second. One of the nice features, but one of the fallbacks, one of the failures is when this goes off, it does not disrupt the tube. The tube remains intact. And you see guys trying to hold the tube when it's shooting. It can be done, but if there's a weak layer or something like that, or a crack or a bubble, you may get a little perforation and you may get a little jet of flame from that dust explosion coming out, can burn your hand or start a grass fire. So you do want to be careful with where you put the stuff. Generally in our rock environments, not a big issue, but you should be aware of it. The initiation part of the stuff. In-hole detonators are designed to initiate a cast booster or something similar. You could be initiating det cord, for example, but generally we're shooting cast boosters with these in-hole things. Surface blocks, the surface delay detonators, are passing a signal to the next line, the next detonator, and they're initiating the in-hole dets. So they're there to sequence the blast. So here on the left, you see in-hole dets. They've got a couple of links of these things. On the other part that's hidden underneath, there's a white clip there on the one on the left that hitches into det cord, for example, or you may just attach a surface type detonator to the tubing itself. Here's a surface delay detonator. On one end, it's sealed with a flag tag. It's got a clip so that you can initiate this with cord, but on the other end, it's got a low strength delay detonator there, and you slip the tubes through there. We'll see that in a second. Here's a combination unit, and I had to throw these out. Tom Molden out there in western Colorado always used to say, I don't know what to call these things. They've got a high strength in-hole detonator on one end, and they've got a surface block with a delay on it on the other end. Now this might be 350 milliseconds like this one is on the outside and the 25 on the surface there. We call them easy dets. They've been called handy dets. They're happy dets is what Tom used to call it. Just a range of things, but it's a two-part unit. And the way it works is pretty simple. We'll see a picture of it in a second. First thing with these systems, like I say, not susceptible to the introduction of outside energy sources, extraneous electricity or whatever. They're easy to learn and use. That is huge in our business because you may have pick up labor to do stuff. It's also where you got to be careful. You can get a good variety of delay patterns out of them. They are fixed timing, but you can get real good variety. And you can get some lower inventory costs on these things than having a whole raft of, for example, electric detonators, which are all fixed delays, but you have to have a whole range of them to do it. These you can have one unit and you put them together and you can get multiple combinations of times. The downside, you can't test them in the hole, and the only way you can check the pattern is visually. You got to walk the pattern and see that everything is connected, and that's where some tricks come in. Quickly, I don't care about 90% of what's on the slide. The bottom end is what I'm looking at here. For the surface detonator on the left, there's no PET in the bottom of the thing. It's got a lead azide charge. It's a light duty charge. It'll shoot tube and things like that, but it will not shoot cast boosters and it will not shoot det cord and other things like that. Here's the downhole detonator. That's got PET base charge in there, and it's 3 times the energy down in the hole roughly for a number 8 strength. That's what you're going to use to shoot a cast booster, to shoot det cord, or to shoot some dynamites and high-grade products. The next big thing, I talked about visual connections. So for det cord, you got to have compatible core loads, and usually you're talking 18 grain a foot and higher. But when you've got compatible core loads, so that you've got enough energy in the donor and enough energy in the acceptor, going to the acceptor there, it'll shoot through. Square knot's the obvious easy one, you know, left over right, right over left. You get a nice connection there, and it'll shoot right through it. A single wrap clove hitch, a lot of guys are very used to doing this. They can do this in the dark, in their sleep, whatever. So you run across it like that, so the yellow cord comes in as a trunk line, and it'll shoot the pink stuff down the hole. Okay, here's a double wrap clove hitch. A little more secure. The guys use it all the time. Works great. Again, yellow the trunk line, and you've got the pink cord going down. The feature that's important in all of these is, and you don't see the end of the cord anywhere, you don't see the tails. In this case, on the square knot, you see the tails of the thing are parallel to the cord, so it's tied together that way. The tail, assuming it's on the top side here of the clove hitch, that's out perpendicular to it, and the down line is perpendicular to the cord. Similarly, here you've got a tail that's perpendicular and down line perpendicular. That's a big feature because as you get the energy running in along the cord and that fireball, you don't want any more than necessary to go down the hole. You don't want it coming off, throwing energy off at an angle and catching something. Hitching up to a detonator, this is easier. Hitching up to det cord, you can wrap the cord around it and then tape the thing up that way. You can just run a single line of it and tape it up here, but you want to get a business end of a high-strength detonator hooked up to the cord to shoot it. Shock tube systems, a little bit different. You need a combination of heat and ignition, heat and spark in there. One of the easy ways to do it, obviously, is the Rothenbuehler type equipment. I've got a picture of a couple of them from their website, and you can stuff the tube in on the side and away it'll go. On the left side, shot shell primers, whether a scorpion unit or a mushroom starter or something, going to use a shot shell primer into the system. You hitch the tube into it, and when you fire the thing, you get the right amount of energy, of heat and spark to get the tube going. And obviously, he's got to hitch through here to keep the thing from flying loose and getting a poor transmission of energy. That's the big part to worry about, is the transmission of energy. Like I said, cord angles and things like that. Here's a good one on the left, using that clip with a shock tube system hitched onto the cord. You got to keep it at a right angle because the energy coming in on the cord here is got to transfer to the tube without disrupting part of the tube further on down the line. So here you've got the cord shooting through here, a poorly connected clip here, and the tube is supposed to shoot down here, but the angle it's at, the ball of fire from the cord, which shoots much faster, is going to come out this way, and it has the potential to cut off that tube before it's fully initiated and the signal's running on down it. So it's not a right angle connection. Similarly here, there's the cord running across, but there's the clip, and we're letting the tube, the business end of that tube where the signal's got to go, wrap around and potentially get cut by the cord before it even makes it to it. So you've got poor alignment there. You may or may not get that to shoot on that side. When it shoots here, the tube over here may already be damaged. So you've got to be careful with how you align these tubes and cord. Proper connection here, place the cord in the clip, push it in, clip it down, get it at right angles, cinch things up. If you're doing multiple connections, take up the extra slack by pulling the tube through a little bit if that's what you want, but keep them at right angles so that the business of transmitting the energy along the cord hits the tube and it runs through. With the easy debts, but I call it the happy debts, they all tend to work about the same way. The hole-to-hole connection part of the unit is basically clipping that tube in there properly. And you say you clip it in, you get it in fully through there, you slide it on down towards the collar, which gets rid of any grit or stuff that might be in there and gets you a good connection in there. And like our marketing people would say, clip it, grip it, slide it, shoot it. Get a good connection in through there and don't have the thing all tangled up. You don't want to have the thing just lying on the tube. It's never going to make the connection. There's not enough energy in there when it just lies there to make that tube shoot. In the middle there, you got to have it in all the way. Out on the edge, you don't have enough energy because the energy is largely directed out the top of this block. This one, where you've got crossovers of tubes, you can fail to have that thing shoot properly there because you don't have, again, the energy transmitting from the block, from the low strength detonator to the tube. There's a good one, and it will shoot. Most of these things will shoot 6 tubes in there if they are in properly, securely, well aligned, that sort of thing. So enough beating on that. Out onto the bench, it's a visual check, and you'll see these pictures several times. Baron's going to talk about these because this is a part of the liability side. When you go to check it, a nice, neat connection like this lets you see where the signal's coming in. It's going to hit all the tubes it needs to hit here. It's got a line going down a hole and something maybe going off to the next hole. Similarly here, what they're doing is they've got a nice clean connection here. Things going down the hole or running out that way, running over here. You can tell what's going on in here. This tangle starts to bother me. And this is a better shot of tangled mess. You don't know what's going on. If you're going to walk up to this at every hole on a pattern, you've got to figure out what's coming in, what's going out. You got to look hard to see that everything's in there properly. This is putting you at risk because it's just hard to visually check. Out on the bench, the keys to it, frankly, and Baron will hit on this too, is plan time to check the hookup. You've got to have time with these things because it's a visual check. You got to walk and look at every one. I always say don't have anybody but qualified blasters do the hookup. They're easy to do, but you want to have people that know what they're doing with it out there. And the other part is have someone else check your work. Blaster shouldn't be forced to go check his own work there because you may not see your own mistakes or the things that you repeatedly do. The other part, a big one, don't connect the lead in until done and everybody's retreating there. And the other part, obviously, for photos is have the right PPE on these people. On that last one there, don't connect. If we drop back for a second, these are easy to use, they're simple to use, but it takes more training than we're going to get just in this presentation. So you want to get proper training on these things to cover all the aspects of using these products. That's all I'll say on that one. Timing considerations. Here we get into using it. The core part of the thing is that you've got the surface delay times plus the in-hole delay times giving you a whole firing time. And it's that trick to these things that you have to understand in putting them to work. Timing is talked about in terms of hole to hole and row to row. Here we're saying, okay, I've got surface plus in-hole equals the firing time. So if my surface times are up here at 0 as I start, and I'm adding nothing, it's instantaneous, say with cord, as I go across and I shoot all 3 holes that have 600 millisecond in-hole delays, what's my firing time? Well, obviously I've got nothing on surface and I've got 600 in all the holes. So it should be 600 milliseconds that they're all firing at. Here's one where I've got 100 millisecond delays on surface. So I may cut the cord and put in a 100 ms connector, or I may be using a tube system that gives me 100 milliseconds between holes. Again, my surface time plus the in-hole time gives me my firing time. And for this, I'm going to shoot the first one at 0, but then I'm going to add 100 to get 100 plus 600 is 700, and then another 100 on that 600 gives it 800. So you got to remember the cumulative time on surface and then the in-hole delay to get the totals. Here, if I change up the delays in the hole, it highlights that. Starting here on this side again, I've got hundreds on surface and I've got different delays down the hole. So my firing time for each of these will be obviously 300 for the first because there's no delay there, but I pick up 100, add it to the 100, get 500 there, 100 and 500 gives me the 700 there. So not too tough once you get into it. The trouble with this is we tend to be using something like 9s and 17s and 42s and 65s, and that's where the math gets more interesting. Here's a pattern, for example. I've got 500 millisecond delays down the hole, and I'm using 25s and 65s on surface. Question is, what's the firing time of this last hole over here? This is the first problem that's in that workbook. If you've chosen to download it, you'll see it there, and if you've downloaded the solution stuff, you'll see those in a separate set of slides. But again, I'm just going to add up, for me, the surface time, and then add in the appropriate downhole time. So 0 there, 25, 65, 25, 25, plus the 500. And that gets me, there again, 25, 65, the 25, 25, and the 500, firing time of 640 milliseconds for that last hole that I've shown here. Here's how you hitch up some of these things and what a pattern might look like. This is obviously too neat to be anything that I work on, but this is where some of it works. You got a point of initiation here, signal comes in, and it's going to fire a collection of tubes, some going down the hole and some going over to the next hole and also going to the next row in this case. So we get a delay here, we've got a downhole delay, and then we're starting to spread things around. This shows nice, neat connections because it's got a little handful of rock or dust or dirt or whatever holding the tubes down so that the blaster that's checking it can see the connection, can see lines going down, can see lines coming out to the next holes, and so forth. If it's decking that you're doing and putting multiple units in the hole, it gets to be a mess on surface, and you've got to keep track of this. That's why you don't want to jump into this without some experience or good supervision, good training on it. But here, if I've got, say, 4 decks in the hole, they're all the same delay in the decks. Okay, it's a 500 down the hole, but if I've got this 25 millisecond block coming in, and it shoots that first one, and then I chain on out to the next one, and chain to the next, and to the next, and then finally a signal going to the next hole, I can achieve different timings down the hole with the same product. There's that inventory deal. And I can just connect them up across there. And I can hook up a whole pattern by putting a collection of surface delay units together with these 2-part units. The timing, and I talked to Rio about this a little bit. There's a lot of there's a lot of options here for what you could put in your blast hole pattern diagram. Some of the key parts of it, though, you've got to have a north arrow in there, like Kurt says. You've got to have, especially a point of initiation. That lets somebody picking it up orient themselves and figure out what's going on. The other part that's key would be some kind of legend, just show the different delays that you've got, and whether that's just arrows or slashes or X's, and telling people what the downhole delay is useful. The other part that's handy there, sooner or later, you've got to identify somebody that's shooting, that's doing the shooting, that's legally allowed to do it. Should be telling people about where it is and when it is, something about the pattern that you're doing, the delay pattern in there, where the free faces are, where you expect it to move, for example, and any exceptions to standard loading, like dropped an extra booster, double primed this hole, had a cutoff, whatever it is, somebody's got to be able to recreate the blast in their mind or on another piece of paper with the information you give them. So another concept with shock tube systems or non-electric systems is the idea of a burning front. If we shoot over here and we've initiated over at this front end here on surface, because these surface delay times here, if I've got 42s running across, like this, you can see at a point in time, I've fired here, 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 here. I've not yet fired a surface delay block, but I'm already showing by my downhole firing times with 200 milliseconds in the hole that this hole is firing. This one's burning, 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 burning. This one, like I said, doesn't have the signal on surface and it does not have the signal in the hole. So you've got to watch where the progression of initiation is on non-electric systems. Another way to look at it here, if I'm showing detonation of holes here, these holes I'm showing as being initiated, that is lit up, and I've taken this pattern and run back up and tied in another bench up above, for example. It's mostly all lit up here, but for example, where I've got holes detonating on the right side, I still have not lit up my pattern over here up top. And if I threw stuff up this way, that could cause me some grief. We'll see that again in a second. The mode is talked about as fast or past. Past, partially activated sequential timing, that's where the risk comes in. Fast is you've got everything activated before any hole fires. And by definition, most electronic gets typically give you fast timing. That is, everything's cooking in the hole before it's ready to go. But with non-electrics, you've got to watch out and watch where things could get thrown. So here, I've got a massive portion of the shot starting to go down below, and I still have not lit up part of my pattern up top there. Not everything is activated, so I am at risk of throwing things and cutting stuff off. It's just part of the deal. Last one, time difference between the first and last hole firing is blast duration. Some reports require it, but there it is. Some of the considerations when picking your delay timing, obviously you've got to pick what's on the truck or what's in the magazine. You're limited on lengths and delays. You may be limited on the weight per delay you're allowed to shoot, so you've got to design accordingly. You've got to be ready to provide the time and the manpower to connect and check your pattern. You got to look at fast and past timing, like we said, and then most importantly, the blast environment. You know, the obvious things like clearing people out, clearing equipment out of the area, but also picking your timing to suit the geology, as Kurt said. Looking at where things could throw, looking at where you could have cutoff potentials and so on. The 8 millisecond rule business, and Vince has got this easy because with electronics, you can get way past this far more easily. This goes way back to 1960s era U.S. Bureau of Mines research. They said in a nutshell, if a minimum of 8 milliseconds is maintained between blast holes, the vibration effects are not additive. That is, if you keep at least 8 milliseconds between holes, you can count them as going off separately. If it's less than 8 milliseconds, you got to add them up and say that's all going at the same time. So typically we report a maximum total weight within any 8 millisecond window and calculate the scale distance with that weight. So here I've shown a simple pattern, not a lot going on. I've got obviously 9 millisecond delays somehow here and nothing in the hole, but I've got 9, 18, 27. Well, when this one comes back here with a 17 millisecond delay and I get 26 total, I've got 26 and 27. Those two holes are considered to be going off at the same time. That is within the same delay window. So if these were 250 pounds a hole, that would be 500 pounds per delay that I would report and use for my scale distance calculation. Here's the next problem for you in there. I've got a pattern that's laid out here, and you can see how it's tied in with the red and the green arrows. Here's my legend that tells you that I'm using 17s and 25s with this, and I have a 350 millisecond downhole delay. One of the possible problems that you could be asked for is to time a pattern on a blaster's exam, or you may have to do it just to figure out what's going on your pattern, and then decide if you can add another row or add some more holes or how to make adjustments. So the question for you is, time this pattern, figure out the delay times through to the end. Well, for me, I usually save the downhole delay till the addition at the end because it's telling me they're all the same. So I start looking at the surface units and say, well, I've got 25s on surface. So obviously if this is going off at 0, the point of initiation, then 25, 50, 75, and so on all the way down, and start to do the math as I come back on the echelon with those 17s. And I end up with this. So I add in that 350 downhole to the 0, and this was 25 plus 350 and so forth. And I run out my timing that way, and I add in the 17s and come back. Down here on the other end, I'm zigzagging back with 17s and 25s again, and I get a total on this that looks like that. Why would you do it? Well, you're wanting to see if there are duplications anywhere. I usually start looking at for holes within 8 milliseconds by picking an easy number, like a 500 here, and then go looking and saying, well, let's see, I'm getting 484, no, but I got 509. Well, that's more than 8 milliseconds apart. I'm good there. 492, that's 8 milliseconds apart, so I'm good there. So this pattern looks pretty good to me, 1 hole per delay. What happens on this if you add a 4th row? And if you've seen the workbook there, you see that you've got room to add something to it. If you put in a 4th row here and continue out with the 17 millisecond on echelon, you'll find that that 4th row pushes you out, and there's my 500 going there. Back here in that 4th row, I'm going to pick up a 501, and it actually matches all the way along, 475, 476, 526, 525, and so on. So I've got a pattern of 2 holes per delay as this thing works across. And that's what I have to do with the thing. The other one that Rio brought up that's a really good one for folks, no matter what system you're looking at, is where does the vibration energy go? If you're worried about pounds per delay, it's because you've got an issue. You're worried about something. On this, when this shot goes, where does the energy go? Well, to me, the first thing that happens is it opens over here and we progress over and back, is we tend to get a collection of holes shot, and we open a hole. We open up the pattern over here a little bit. If there's a free face along the left side, terrific. If it's just opening at a corner, well, sooner or later I'm going to shear off some of this, but I'm going to open a hole in here, which is going to tend to prevent vibration energy from the right side of the shot from going very far to the left. The other thing it's going to do, once I've got that hole open as it progresses, I'm adding in energy through these other holes firing, but I'm building up an impulse or series of vibration impulses that are going this way. So lots of guys will say, okay, I'm going to shoot it this way. I'm going to shoot it away from that corner because I don't want to damage it. I'm going to shoot it north to south so that I don't push energy to a neighboring mine or a housing subdivision or something to the north, but I'm going to look at where the energy goes. I'm opening out here, and yep, this material is going to be moving out this way, but the impulse, the building impulse, is going to be going, in this case, to the right. Okay, here's another problem for you. Find the number of holes per delay. This is a common one for blast exams, where you say, hey, tell me what you got. And I took this old but very simple pattern here and said, look, you got a point of initiation on the right side. This is a trunk line system with cord, and I've used delays, surface delays here, to break up the pattern. So everywhere you see an X, I've got a cut in it, and there's a delay there. They're the same time delays, and they're the same time delays down the hole on this. But the question is, how many holes per delay are going off in this pattern? Well, pretty easy. Anywhere along here where I've got 3 in a row between a cut there and a cut there, I'm going to pick up 3 holes per delay, 3 holes per delay, 3, 3, and so on. So my maximum of pounds per delay would be 3 times whatever's in every hole. Okay? Let's take that same problem now and put some other numbers on it, because this is typical for a blasting exam. And this could be shock tube, it could be detonating cord, it can be a lot of systems, but I'm focusing on the electric side. If all holes have the same delay, and you see that I've got the thing cut up that way, again with the det cord and those delays, how many pounds per delay do I have firing on this pattern? Okay, well, it's going to be pretty simple. We already saw that it's 3 holes per delay, so we'll save that 3 here for a while because we know that. Okay, I've got 2-pound booster in each hole, 9-inch holes, 55-inch band height, 22 foot of stemming. So pretty quickly I can see with the density there, I can calculate my weight per hole. Formula for that is pretty simple, pounds per foot, which I'm going to multiply by the column height, and then I'm going to add in the booster weight to get the total pounds per hole. So that's going to look like diameter squared times that 0.34 times the density will give me pounds per foot. I'm going to multiply that by the column length, and I'm going to add in the booster weight. And I can do it with a bunch of brackets to clean it up, but I'm going to dance on the high wire and tell you I remember how to do that. So 9 squared times that works out to 36 pounds per foot. I've got 33 feet of loaded column there, and I've got 2 pounds of booster weight in there, because most exams want you to include the booster weight, and you certainly include it on a blast report. So it comes out to about 1,185 pounds per hole. I said I'm going to remember the 3 holes per delay. So my weight per delay is the number of holes per delay times the weight per hole is 3 times 1185, or just short of 3560, where you round off or whatever you do. But 3,555 pounds is what I came out with. Okay? And since this is such a common problem out there, let's take a look again. Here it is. I'm going to let you do this one for a minute. Same pattern, but I changed up some of the numbers in red there. So what do you get? Well, if you haven't downloaded it, you know that you're going to go through the same thing. Some people will have picked up their calculator and started trying to do it that way. That's going to get you in trouble, I will tell you, on an exam. So I tend to write things down. Again, I took the light blue stuff, the diameter squared times that factor times the density, gets me 6 squared times that, gets down to 15.3 pounds a foot. The column length is going to be that 45-foot bench, minus the stemming, but plus that 3 foot of subdrill. So a total of 30 foot of column loaded there, and 1 pound booster in each hole, 461 pounds per hole. We said we had 3 holes per delay. So multiplying that out, 3 holes per delay times the weight per hole gets me 1,383 pounds per delay. Okay, typical problem on most exams or most blasters going out trying to figure out a pattern and decide if they need to cut it up some more or where they're really at. So the systems themselves and doing delay patterns, and I'm going to go through these quickly, but there are elements in here where the geology comes to bear. Typical patterns, you really only have about 3 styles. There's an echelon where you're pulling it off a corner and peeling it out. You can change the shapes, you can change a few things about the opening, but that's what you get. A V-cut or box cut, where you're opening typically in the center, and it's going to open up in the center and push out with delays running out to the left and right sides, or a center opening, whether it's for sinking or a drop cut, or for that matter, for a face round underground, where you're opening in the dead center of the thing somewhere, and the initiation is going to extend out top and bottom and out to the left and right, and you're going to open it that way. Let's take a little closer look. One of the concepts right away is timing out the pattern. We saw that. Okay. In this case, I haven't bothered to worry about what's down the hole. We could just treat these as all going at 0 delay down the hole. So our surface timing is what matters here. What you can do is you can draw a line between points of equal time. So right around 109 and down here, a little bit more than 100 is 109. There's a timing contour there, and perpendicular to that, where the arrows are pointing, that's the direction of movement. Okay? And that's a function of the delay times and just the way that it works. This particular pattern, it's a standard one, not the best one, but a standard one there. You could run this pattern 3 rows deep, like we've shown, and infinite length. It can run out to the right as long as you want, and you won't get more than 1 hole per delay. Or you can go up to 5 holes wide to here, cut it off there at that 100, and you can go infinite depth, 6, 8, 26, 28 rows, and you still only be 1 hole per delay. When you jump out to a 6 hole in a row, the 125 up there starts to catch up with you, because when you get up into that 4th row, you're going to be picking up another hole here. That is 84 plus 42 is 126. So you're going to get caught. Let's take a better look at this pattern. I can achieve the same kind of timing on it. That is 0, 25, going down the control row, and 42 between rows by using 17s and 25s tied in on an echelon. The advantage of this is that if I have a cutoff somewhere here, for example, let's drop back. If I have a cutoff in this pattern somewhere, like here, if I cut out that that delay and suddenly I'm not giving a signal to these holes, the signal can still go around it and throw material from these holes over top. And I could do it on the face row and have a worse problem. Cut off the the last 4 rows on the face row, the signal can still come around and throw material over top of undetonated holes. So far preferable to run a control row down the face, the free face, and run back on the echelon. If something cuts off here, then I don't have holes behind it going off. I have a small number of holes covering me up here. It shuts down the rest of the pattern, and I've got a far easier job cleaning it up. Both of them give me that same timing contour or the direction of movement that I'm showing there. If I adjust the delays, I can change that direction of movement, the angle of movement. So for example, here, first one, if I use 42s going back, I get this coming off at a fairly steep angle. As I increase the delays to 67, 92, 117, I start to push out and make a much shallower angle for movement on this. And depending on my material and what I've got to shoot into, the hole I've got to shoot into, or the equipment that I'm shooting for, I may want to adjust it to make that work. Here's a V-cut one. This is a simple, very simple one because it's got no difference between the left and right side, so it's just a mirror image. The symmetry here is obvious. I'm running back from a starting point here with 25s all the way through, and I'm throwing 17s out the side. I've got a fairly shallow angle here, flat angle, and I'm shooting 3 holes per delay. As you can see, I could fix that by putting in, say, 9s and 17s on one side or the other, and making it shift a little bit. This one is labeled as poor timing sequence, and I added the question mark to it. This is a tight V cut, and we're starting up here at the top center, coming back with 25s, but we're using 42s to come up to the other holes out to the left and to the right, and it produces this very sharp V, if you will. The previous one was a very shallow V, like that. Here, I found them fairly tight, and the question, or the comments that were made on it was the fast burden delay, that is these 25s, don't create enough relief for the adjacent holes. So I have not got this moving very far for these holes to move out and give this some relief. It says the over-confinement will produce hole disruption. Lack of forward movement could produce undesired vertical movement. The trick is, for some materials, that may be what you want. For some digging operations, that may be what you want. So you've got to decide what works. In coal, for example, some people do this kind of thing. They may vary the times, but they want it to hump up in the middle, pull into the middle, not push out on the side in the ditch very far, and to pull away a little bit from the high wall, but they've got a big shovel that's going to dig it. They want it humped up, and the hard, brittle nature and the fracturing, cleating, the geology features of the coal may make this work for you. And they want to shoot it fast so that they don't get disruptions between the holes. Okay? For that material, it may not be over-confined. So it's all very dependent on the material. Here's another V-cut, but it's using a zigzag pattern down the center. So we started here, and we've got a control row that zigzags through it. Very flat angle for the thing moving out. Not an uncommon pattern. Here's your 1 hole per delay. You can go 10 holes wide and as deep as you want to go, as many holes as you can shoot. And if you do very small holes, this might be a good-sized ditch, or it could be stripping shots, something like that. Here's a center opening, very quickly, opening in the center here and progressing up and down and out to the sides, left and right. And in this case, we're showing multiple holes going per delay, and this one 10 holes per delay. But it's just a way of applying those delays and those detonators the way you want. You may want to add some timing in there, and this is what the blasters will be looking at, is how does this work? How's this working for me? How's it going to work on this shot? That's why you might time out the pattern. You may want some time at the end of the hole, the end hole on each row, or the back row. You may want to add some time progressively as you get deeper and deeper into the shot because you're waiting for the material to move and you don't want it to stack up and give you a hump, or anywhere where the timing gets crowded, as we say, to prevent something shooting ahead of material that has more holes or hasn't moved, or if you've got uneven numbers of holes. So there. Last one I had on this stuff, non-symmetrical or very difficult shooting for non-L system is in dilution control, or where you're trying to separate ore and waste. So if I'm trying to work in this yellow, hard to see yellow band here, and pull the good stuff, the ore, together with my delays there, and let this other material push away with the red arrows there, this is going to be a pain in the butt to do with non-electric system. This is where you get over to electronics and you really start to love the power of technology. But that's where that is. Some words on safety. I'm going to pause there and see if there are any comments or any questions. If not, I can quit now or just hit a few safety things. What do you got, Rio? Anybody have any questions so far?
I think you're good to go, Brad. Go through the pyrotechnic safety.
Moving ahead. Couple of quick ones here. These are by the book, some tie-ins, suggested hookups for non-L units. I showed running a control row down the face and running back on an angle from the control row, but managing the number of holes that could be in a difficult situation if things went haywire, if you had a cutoff or something like that. I point at the advanced open pit blasting manual, but a lot of guys will look at their experience and say, you know what, in this rock, this material, this works well for me. Okay, some tie-in connection stuff. Connections between the holes should not be made until you're ready to clear the site. That means you got all the trucks off there, you've got the skid steers and all the visitors like me. You've got all the trucks and everybody else out of the way, and you're ready to hook it up with minimum number of feet tripping over stuff that's out there. You can use a barrier if you're going to demarcate loaded holes from where you're actually doing loading and you're working, stuff like that. That is separating the activity from the surface detonators. The big part here is keeping the equipment and all the detonators apart so there's no contact. We've had issues over the years where trucks drive over tubes, drive over wires, drive over cord or blocks, and they cut or they potentially set them off. It has happened where they've got the shock tube tangled into rotating parts on a pickup truck or an Explorer, and they had a snap, slap, and shoot incident where the hole was shot, and the truck that was tangled up in the tube in that hole was blown about 70 feet in the air. So not a good situation when you mix equipment with loaded holes. Minimize the number of people involved on the tie-in side of the job. You want to know that they're all qualified to do it, and they're going to do it all the same way, and that they're going to do it well, because it's going to cost you time to tie it in, and it's going to cost you time to go back and walk and look at it. It should all be supervised by the blaster. The blaster cannot abdicate that role. You don't want to stretch the tubes or string it out so tight that it's a banjo for you there. So you want to allow for movement during the thing. You should be able to check things without picking them up. And I'm pretty sure that Barron's got stuff in there and there are comments elsewhere here about how you got to check it. And then, like I said, avoid checking your own work. Here's one, similar kind of pattern to what we saw. Here I've got the connections here, nice neat connections and tails and so on, so I can follow what's going on. Like I said, two holes, but you might want to add another service delay unit to give you reliability. And you do it the same way. You hitch them up, you run them out to get the next row and to get the next hole and the next hole and so on. Okay, make things easy for yourself wherever you can. Here's one where the liability side comes in, or put differently, where they've had so many problems with the systems that they've got to build in some kind of insurance, and they use paint or tape on the blocks to show that people have checked it and inspected it. They may have people video recording walking the pattern to show that it is right, it's all going to work, and that's a good layer of insurance for some people. Extra delay units as tattletales. We showed some patterns where I've got to figure out how to call the all clear, but I can't get out there to see it because I've moved stuff or I need a way to be able to check it. Put in an extra block out on the end to show that you've had continuous firing out to the last hole and beyond is very common. We'll see that in a minute under a map. And the other part, don't start connecting the lead-in line until the safety zone, that is the blast area, has been cleared. You don't want people in there still waiting to get out or waiting to move a pump when you're already hitched up and tied in and ready to start shooting. And the other one, like with cord, spool out the shock tube line or cord before connecting to the blast. Here's putting a mat in. This is one of the tough parts with this system, any blasting system for that matter, because when you put these mats down, they can disrupt the connections and the things that you've got on surface. It can happen with electronics as well. So the trick is to find out how it can work. It's a long, slow process to put these in, and you're trying not to move and disrupt the connections on there. You might want to put some dirt on top of the holes so that then you can put the mats on it and not disrupt the connections. But in any case, you probably want to have some tattletales, some lines from the shock tube system extending out beyond the end of the shot so that you can see that everything is fired to this point, to the end, before you get too far along. And that's it.
Okay, great. Does anybody have any questions they'd like to ask? You can raise your hand or you can write your question into the system here.
Hey, Brad, can you just explain again what is the purpose for the downhole delay?
The purpose of the downhole delay, well, the purpose for all the delays is to get the material to fire when you want. You're always looking at applying energy to a mass over a period of time. So a surface delay is a very simple way of breaking up the holes. The downhole delay lets you delay, if you will, when the shot starts to actually go off and starts to move. And that's where I said the fast and pass systems. In a partially activated system, you've got downhole delays, which allows a hole to go off, but you may have, depending on your choice of surface delays, stuff still being initiated on surface a few rows over. So you want to have some time in the hole before everything starts to move, starts to pull at connections, starts to pull at, whether it's tube, cord, or wires for that matter. You want to have the thing set so that the holes don't all go off too soon for the surface delay and disrupt it, cut it off.
Okay, so reduce chances of cutoffs, the main purpose for it.
Main purpose for the downhole delays, first in terms of timing, is to protect what's still being lit on surface. If you're starting to deck things downhole for some reason, then you're splitting up your charges. But the big thing in both cases, whether it's decked or not, you want to protect the initiation system on the surface from the holes actually firing and starting to pull things apart.
Okay, thanks, Brad.
It doesn't look like we have any questions.
Okay, let's go ahead and break and be back in here at 30 minutes past the hour. Thanks, Brad.
Okay, let's go ahead and get started. I'm going to hand this over to Vince.
Okay, so you should be able to hear me. And I'm gonna get the PowerPoint going here. I'll just have to do a quick check to make sure I'm sharing the correct screen. So does the opening slide of the PowerPoint show electronic initiation systems?
It sure does.
All right. Well, thank you all for giving me the chance to present today. My name is Vince Sloan. I'm a technical consultant with Dyno Nobel. Previous to joining Dyno, I was a mine engineer for Rio Tinto. Wore a lot of different hats there at the Bingham Canyon mine in Utah. Then I came over to Dyno Nobel, worked a few years in the electronics group, and then last year I moved over here to Indiana, working in the technical group. Today we'll be looking at electronic initiation systems. So for those that are not familiar with electronic detonators, we'll kind of look at these systems as a whole. It includes all the hardware, software, and detonators. Then we'll compare their construction to that of pyrotechnics and electric detonators. And then we'll also kind of look at the statistically how the delays perform across these three different types of detonators. And then we'll talk about some of the ideas where this increased precision and accuracy can really be applied. So the outline there, as I said, we'll go over EIS. Sometimes these are referred to as EDD, electronic delay detonators. But within Dyno and some other companies, we refer to it as EIS because there is associated hardware and sometimes software with these detonators. We'll look at the detonator delays, how they do with accuracy and precision, and then what you can do with these accuracy and precision, because there is going to be a difference in the price point of electronics versus other options on the market. So you're going to have to be able to apply the advantages to somewhere where it's going to drive financial benefit for your company, or it's really not going to make sense to be employing electronics. We'll kind of be looking on operational benefits in specific with these examples, but I will touch a few along the way on some safety benefits, and there are actually mines out there where the safety advantages, even though maybe they're not getting the operational advantages, the safety advantages, what's driving their use of electronics, but that's not the main focus today. And then I'll provide a few final thoughts, and I have a few questions just to go over, make sure you guys understand some of the finer points of electronic delays. And so first, what is an electronic detonator? So the name comes from the fact that the delay is achieved electronically, not pyrotechnically. So as Brad was discussing in his presentation, you have the electric delay or electric detonator on the market and the non-L. Those detonators are actually named for the mode of initiation. One is initiated electrically, one is initiated, originally the name was for non-electrically. Brad kind of made a good adaptation there. Now it's non-electrically or non-electronically. Electronic, although initiated through electrical energy, is named for the way the delay is achieved, and that's through electronic programming. The detonator is going to contain an internal computer chip or an application-specific integrated circuit, an ASIC. That's going to control both the initiation time and the communication back to the controlling hardware. It'll have one or more capacitors where the energy is stored until firing time. And so the characteristics I'm going to be listing, although I'll be showing Dyno products for the most part, these are characteristics and conditions that are going to be found across all systems on the market. So across all these systems, three conditions are going to have to be satisfied before you can detonate one of these detonators. You're going to have to assign a firing time in the detonator memory. These come from the factory. Typically, I'll say typically with a blank firing time, so there's no firing time in the detonator memory for the detonator to be fired. So even if it met the other two conditions, if it didn't have a firing time, it would not fire. A sufficient charge has to be provided from an external power source. This powers the circuitry for communication and also provides the voltage to fire the fuse head within the detonator. And the fire command must be received from the control equipment. So the electrical energy is usually sent in such a way that more or less acts as the encoded signal to get the detonator to fire. So it's not enough just to have one of these three or two of these three. You actually need to have the firing time, a sufficient charge, and the fire command received. Here's kind of a breakaway of the construction. This is from the latest edition of the ISEE Blaster's Handbook. We'll start there at the base at number 1 and work ourselves up. So much like the downhole detonator that Brad displayed, you'll have a base charge and ignition charge. So you have the two different charges there, the lead azide and the PETN, because these detonators are used, they can be used on the surface to initiate things, but typically downhole, you rely on them to set off that cast booster. You'll have a fuse head, and then within this one, you'll have the integrated circuit chip, which is controlling the communication and where the delay is stored. You'll have a capacitor, which is where the energy is stored. So when that energy is first provided from the blast hardware, it is charging the capacitor. Then the capacitor will later release that energy based on the program delay. You'll have typically a filtering safety device, which is usually a resistor or a combination of resistors that's filtering out non-specific energy inputs. So this is where I'm saying it's not enough just to provide the energy. If you provide the sufficient energy, you're either not going to fire the detonator, may damage it, and if you try to overcharge its fire, you're definitely going to damage it. You'll have your incoming leg wires, and then you have some kind of seal plug, because with all the circuitry in here, dirt, water, any ingress of that is going to damage the detonator and most likely prevent detonation. Kind of a simplistic thing, and I don't want to spend too much on this because Brad did a good job covering it, but what we're driving at here is with the, they list it as the electric pyro. So I'm going to date myself here, I'm a little bit younger. I've only seen electrics a few times, and it was actually on a university campus for a project I was doing, but I haven't seen them in the field. But pyrotechnic delays, the delay element can actually be incorporated into electric delay. So besides just your switchboard, this is another way you could get a delay when using an electric system. Then there in the middle, you'll see the non-L detonator. That again, that delay is controlled by that pyrotechnic delay element there, which is really just going to have a prescribed burn rate. So this is almost being controlled chemically. The length of this is going to determine how long it takes for this charge, this incoming signal to get down and set off the priming charge and then the base charge. So the length of this is what's determining your delay. And then what they have listed as a digital detonator or electronic detonator, you have a capacitor, you're gonna have your delay circuit that's gonna let the capacitor know when to release the charge and fire the fuse head. Just a quick comparison there. Running through the components. So as I said, sometimes referred to as EDD, the electronic delay detonator, but we can look at it as the system as a whole and everything that goes into it. So first, as we've discussed at length already, you're going to need the actual detonator to go down hole. And then you're going to need a device to test, program, and communicate with individual detonators. And subsequently, later on when you're doing testing, groups of detonators can be hooked up and tested to save time as well, as opposed to just testing each individually one. This is known as a logger, a tagger, a programming unit, but it's typically a handheld device that the blaster will have, and that device is used to communicate a delay to the detonator, to read information from the detonator, and run some internal tests with the detonator, make sure communication is sufficient and that the detonator can support the firing charge. There are wireless options now in the market, and more are coming almost by the quarter. But in your traditional electronic system, you're going to have a harness wire to connect the detonators. This is the pathway for communication and for the firing voltage to be provided. So an individual detonator will typically be able to speak directly to your programming unit, or tagger, your handheld device can hook that up. But at the end of the day, once all the detonators are deployed, you're going to use harness wire to group those together, hook it up to one piece of equipment for testing, and then subsequent firing. You'll need some kind of device that provides the firing command and firing voltage. So as a safety measure, your handheld devices typically are not going to have the knowledge to provide the firing command, and also not going to have the capability to provide the firing voltage as a safety measure. That's why at the end of the day, you're going to have a separate device that does have that encoded, that message to, sorry, the capability to send that encoded message, and also the capability to provide the firing voltage. The picture I have here is the DigiShot commander system. So these boxes are interchangeable. One can be used as bench, one can be used as a remote. But the point is, across all the systems here, you're gonna have to leave a device in some proximity to the blast that's hooked directly to the group of detonators that's actually providing the firing voltage. It's kind of based on your circumstances. You know, typically it's probably moved out somewhere 300 to 600 feet. So maybe not to the edge of your clearing radius, but to the edge of the blast area to prevent damage from fly rock, because these are expensive. But the harness wire is not free either, so you gotta balance it out there, put it in a direction away from where you would anticipate fly rock and at a distance to keep it from the fly rock. Next would be your remote device or repeaters as well. So in this system pictured here, boxes can be toggled for one to be the bench and one to be the remote device. Sometimes there'll be two different devices, but you'll have one that you can leave in the blast area and the one that the blaster can take out and will communicate remotely back to that device to do the final testing and to signal to provide the firing voltage. Repeaters I mentioned here, due to wanting to get a greater length away from the blast or maybe needing to shoot around an obstacle, can actually set a repeater that will repeat the signal from the bench to the remote device. Lastly, these devices typically have their own specific software that's going to allow the timing to be done on a computer. So the software can display how the timing is performing. So in the previous presentation, we're kind of touching on the idea of timing contours, and with your blast movement being perpendicular to those contours. So these softwares can be used to see how your timing is performing, but then it starts taking it to the next step where you can actually, instead of put the timing in to see how it's going to perform, you can put how you want it to perform and let it back calculate. So might be a little bit hard to see on the screen there. You can see, we'll call this a timing V. You can actually draw the timing V, which will dictate the direction of movement, then dictate the speed of movement in terms of milliseconds per foot of burden relief, and it'll time the pattern for you. Brad also gave an example where there was almost 2 sinking cuts for 2 different ore dilution areas. That's kind of where it gets a little bit messy doing the timing by hand. Your associated softwares, you know, each system out there on the market should have a software with it or be in partnership with a third-party software that's going to help give you the tools that the software do the thinking for you and almost back calculate the timing in a sense, which is a good feature. This final graphic here is just kind of showing all the things I just discussed put together. So engineer in the office doing the blast design on the associated software. Then this software can be communicated to the on-bench device. So the blaster doesn't have to worry about entering the actual timings to it. They'll be matching a map while they're tagging, but the actual tagging plan is already loaded to the on-bench device. The blaster can then go out there and communicate with the individual detonators to provide their a location and a firing time. And at the end of the day, you can group your detonators up to the maximum limits allowable by the system that you're using. In this case, it showed, you know, the maximum 16,000 detonators, quite a big blast. This would take 10 on-bench devices, and they're shooting it via RF, and they're anticipating being far enough away that they would need a repeater. Just kind of bringing everything together there from the engineer laying out, designing the blast, timing the blast, giving it to the on-bench equipment, and the blaster taking it from there. So characteristics, so these characteristics are kind of a blend of the maximum of what I could find on the market, mostly just from public available information or some information I may have had because I've blasted a majority of the electronic systems available out there on the market. So you have programmable delays up to 30 seconds. That's 30,000 milliseconds. And currently that is done in 1 millisecond intervals. Probably here in the future, you probably have sub-millisecond programmability, just as things get more and more refined and the accuracy improves. And speaking of accuracy, electronics are generally accepted as of having a 1 millisecond to sub-millisecond accuracy. So for example, if you were to program one at 30,000 milliseconds, it's fair for you to assume that's going to be going off between 29,999 milliseconds and 30,001 milliseconds. That's a mouthful there. Expected to have that 1 millisecond accuracy. We'll talk about some impacts to that accuracy later on, but you should expect the 1 millisecond for any delay that you program within the acceptable range of that equipment that you're using. This is a big one here. You're gonna have the ability to test individual detonators and hole patterns. So typical blaster's day will be when they're programming that detonator to give it a location and time, or just the time, kind of dependent on the systems there. You're going to be able to do initial tests and test it individually. Then at the end of the day, those on-bench devices are going to be able to test hole patterns. This is one thing that non-L does lack. You can do your inspection for your hookup at the end of the day, but you're actually not going to be able to see what's going on down hole. Multiple blast devices can be fired from one device. So you'll see this, if you exceed a limit for a device, you can actually typically synchronize 2 devices to blast a bigger pattern. Or if you're blasting in multiple different locations, you can toggle through those or shoot all those devices at once from one device. So depending on what your operational needs are, if you're needing to clear each blast and then shoot them individually, you can do that from one device without having too much headache on the setup. Or these systems are going to have something where you can just actually send the firing command to all of them at once. And if you don't want them all, you want to be able to press fire once, but have some delay offset in that. What you would do is up front, just if you started one pattern at 0 milliseconds to say, and it ends at 3,000, when you start programming that, tagging that next pattern, started at 3,500. So you've built your delay in there. So now you just have to hit the fire button once at the end of the day. They're going to be able to fire locally. So if you're going to fire locally, you're going to be using that blast box that left on bench that I mentioned earlier, typically 300 to 600 feet away. If you're going to be firing locally and not remotely, you obviously probably want to increase that distance based on your firing conditions, because if you're firing locally, you're going to be swiping your blast control key of some sort, whether that's a card or a physical key at that machine. So you'll want to make sure that machine is clear of the actual blast radius, not just the blast area. You can also fire remotely via radio frequency, and then underground options, leaky feeder, and Wi-Fi. Your control equipment is going to have downloadable electronic logs. So this will show, when every detonator, what the time was programmed, and also details on the communication levels and what time the work was done with the detonator and what time things were fired, and the leakage levels at firing time, and a lot of different details in there. So these can be downloaded if you need to troubleshoot an issue, or if you want to double check inventory, or if something looks wrong in the blast video performance, you want to make sure everything was programmed at the correct time. Some people download these on a regular basis and attach it to the blast report. A lot of information there and can be downloaded from the hardware at the end of the day, or at the end of the week, and stored if needed. The equipment typically can hold a fairly good amount of records, but at some point, what's going to happen is it's going to start deleting the latest record found in memory in order to add a new one. I mentioned here, most have to have detonators hardwired and connected to a device. Wireless options have been released to market. You may have seen some presentations. If you guys are at Best in the West, I think 2 years ago, right when this first came out, I know, I'm forgetting the gentleman's name, but Orca gave a good presentation, kind of some work that they have begun doing underground, and also at, I think like a through seam blast they were doing up in Canada. But across the market, everyone's working to get a wireless option out. So it's kind of the future there. Right now it's kind of mining application specific, depending on your mining method. But one of the issues with electronics right now is kind of the sensitivity to having their down wires cut or damaged, or that ingress of dirt or water to the detonator. That's the pathway for communication. So, yep, you can test them, but kind of the two-way street of that is, to test them, that communication path has to be open for testing and for firing. So wireless option, if that, cost ever got to the right point, it could be applied to everything across the market. That would kind of get rid of one of the last hurdles for full adoption of electronics throughout the market. But they're getting there, and it's going to get closer every year. Now, looking more closely at the detonator's delay, so the ability to sequentially blast allows for greater blast efficiency and improved safety, and that's accepted. The two types of delays I'm going to cover here within the detonators are pyrotechnic delays, which is the chemical burn rate, and electronic delays, which is going to be controlled through a programmable delay to that computer chip or to the ASIC. Both of these really differ in their accuracy and their precision, and that's in relation to their nominal firing time. So I say nominal firing time, like for an electronic, if it's programmed at 1,000 is its nominal firing time. When we're looking at the pyrotechnic, we'll want to make sure the nominal firing time, if it's a 25, the nominal firing time will have to take into account surface delays being used and the downhole delay as well. So there's going to be some kind of combination effect. You can look at their accuracy and precision separately, but there will be some kind of combined effects between the use of the surface delay and the downhole delay as well. Now let's look at the definitions of accuracy and precision, and then we'll be able to relate them to the performance of those delays. So accuracy is the question of how close are the individual measured firing times for detonators to the nominal firing time, or you can think about that in terms of just in general statistics or other applications. How close are we to the target, to the bullseye? So in this graphic here, we label this as high accuracy and low precision. So we'll cover precision on the upcoming slide, but for the accuracy here, you can see the bullseye. We have a good cluster of 5 detonators. Individually, some are more accurate than others. One's right there overlapping the red. The one directly to above it is pretty close to the red. So those individually are more accurate than the other 3, but then together collectively, if you were to take that average would most likely be pretty dang close to the center of the bullseye there. So individually and collectively, this has high accuracy, forgive me, please. Precision now is not how close are the values individually and collectively to the center, but how close are the measured values to each other. So in this graphic here, you can see an example of low accuracy individually, and if we were to take a collective average, we're pretty far off from the center. But in relation to each other, we have a really high precision. They're all close to each other. And a good way to quantify this will be the standard deviation, which we're going to cover on an upcoming slide. Accuracy and precision. So this is kind of the best of both worlds and what we'd like to see out of our delay performance. The measured firing times have a tight distribution, and the mean firing time is close to the bullseye. So if I was to look at each of these 5 individually, they're all pretty close to the target. Collectively, the average is going to be right in the middle of the target. And then precision-wise, I have a very tight distribution. So for timing, accuracy, and precision, three factors. And this one's taken, there's a good section in the 18th edition of the ISE handbook. So this slide relies kind of heavily on the work there, but it does a good job summarizing it. So the 3 things we want to look at when we're talking about the accuracy of the detonators and determine probability of overlap. And real quick, for the definition of overlap, it can vary. It can be detonators firing completely out of order, or just detonators firing within, what would be the best way to put this? Detonators firing within the prescribed firing time separation. So typically that's thought about as 8 milliseconds, but if something's timed to shoot 25 milliseconds apart and it shoots within that time, that can be defined as the overlap, and sometimes overlap is defined as detonators actually shooting out of order. So the 3 factors that kind of determine the accuracy and the probability of this happening would be the mean firing time. So over here in this graphic, the mean firing time is the actual average firing time for the group of detonators. The distribution, that's the range of the firing time. So a tighter distribution would mean you're expecting less deviation. So even if things do vary, they vary less than something with a greater deviation per se. So that standard deviation is a measure to quantify the variation. The lower the deviation, that means we're closer to the average, kind of at the tail end of our distribution. For any set of detonators, it's assumed if you fire a representative sample, it's going to provide you a bell curve like this. So that data set's gonna follow what they refer to as a normal distribution. This slide is gonna make a little bit more sense as we get into some of the details on how electronics perform compared to pyrotechnics. One last thing to note here. So the mean firing time, the average, that is the average firing time. There is going to be some difference between the average firing time versus the normal firing time as well. So the mean firing time, typically there's going to be some kind of offset from what was designed, which would be the nominal. And then you'll have the precision as well following a normal distribution, which is maybe referred to as a bell curve. Real quickly, I don't want to get too far in the weeds on this, but when we say it's assumed that it will follow a normal distribution, that means if you fire a group of detonators, you have your average, you should expect 68% of all the detonators within that group to fall within one deviation to either side of the average. So some are going to shoot a little bit later, some are going to shoot a little bit earlier than the average, but 68% should fall within that range there. 95 should fall within 2 deviations to either side, and then 99% is going to fall within 3 deviations to either side. So if we go back to this slide, you can imagine as you're stepping out the deviations here, if you have a smaller deviation, 99% of it's falling in with a much closer range to what the average is there. Looking at, so we won't spend too much time on that. That's kind of what accuracy and precision is and how we are quantifying the accuracy and the probability of things firing as designed. I'm going to touch very quickly on what controls pyrotechnic delays and some of the stuff that's going on, causing some variation in the accuracy and what's driving the deviation percentages. So pyrotechnic delays have a cylindrical casing around a dry chemical core. It's the burn rate of that dry chemical core that's controlling the delay. It's going to be initiated from the explosion of the shock tube or ignition of the master fuse head if it's a hybrid system with that pyrotechnic delay element and an electric det. Core burns at a prescribed rate. So the primary control, obviously, if it's burning at a rate, that's some rate per length. Shorten it or lengthen it if you're wanting to shoot sooner or later. A general rule is that pyrotechnic delays are going to slow as they age. The delays in pyrotechnics can be in periods or in milliseconds, so you can buy it for the specific millisecond and what's available from the manufacturer. Some will be produced in periods ranging from like 0 to 18, and those periods have a set millisecond delay. Millisecond delays may have a surface delay and an in-hole delay. For an example here, 17 over 35, 350. That'd be a 17 surface delay and a 350 downhole. A handy det, easy det, they have different names out there on the market, but that's kind of a combination det where you have the high strength detonator downhole, and that downhole delay is accounting for the burn front and helping prevent cut off and making sure that you've provided the energy needed for the detonator to fire before the pattern actually starts moving. Impacts on the pyrotechnic delay time: age, manufacturing quality, temperature, humidity, internal pressure during burning time, and the manufacturing lot. That's why it's recommended to use the same date code if possible. So this is a graphic provided by someone internally here within Dyno Nobel as an example. So the dashed line is to represent electronic detonators. So a nominal time of 500 milliseconds. You can see the average firing time is right at 500, and you're going to have a tight deviation. These 3 other lines here are representing a 500 millisecond pyrotechnic delay. And what you're going to see from a manufacturer for a pyrotechnic delay is you're going to be given a deviation percent. It's going to typically be something around 1.5% of the nominal time. But they're typically not going to give you an actual number to quantify the difference in accuracy or the difference in the true firing time towards nominal. So the number which manufacturers are giving you, kind of describing the shape of the bell curve and the width of the bell curve. But the average firing time for that lot of detonators is going to be dependent on a lot of different things, including the manufacturing lot. So what's recommended from the manufacturers, we'll say if everything used from October, the thought being the offset from the firing time should be consistent along it. So if we were to look at this red line as October, the anticipation is everything in that, as you get an average firing time, 494, you know, everything is shifted slightly earlier, shooting slightly earlier. But if everything in that lot is shooting slightly earlier, that would mean if you have something that's supposed to go 17 milliseconds off, or have 17 milliseconds separation, both those detonators might be shooting earlier, but they're shooting earlier at the same amount or same difference from nominal, then you're actually maintaining that separation. So sorry, kind of talked in a circle there, but the idea would be, I said, let's try to think of an example here. So 495, so that's a 5 millisecond difference. So if I had something that was going off at 500, then the surface delay of 25 and a 500 is supposed to go up at 525. If both those are shifted back by the 5 milliseconds, then I maintain that separation of 25 milliseconds. And then my deviation is quantified, the bell curve is quantified, but I account for the difference in the accuracy by trying to maintaining the use of the same date code. In this example here, you're showing, well, the accuracy actually could change based on the manufacturing lot. So it's important to use that same manufacturing lot. The precision is a prescribed number, 1.5%, but that accuracy is going to vary. That's the benefit of electronics. The accuracy is expected to be within 1 millisecond nominal time. It's hard to get a number of what the accuracy is going to be up front because so many variables, pyrotechnic, you're only going to get a deviation percentage. So speaking of that deviation percentage, the widely accepted value is 1.5% of the nominal firing time. The mean firing time is going to vary in its accuracy. We'll see an example of that, some studies from the University of Kentucky. It's best practice to use the same date code. I just explained why that was. That's to account for shifts in the overall mean firing time. So let's look at this chart here. I'm showing a 25 over 350. So there's your surface delay. There's your in-hole delay, the 350. Now for the combined effects of using an easy det or handy det and the probability overlap, that takes some in-depth statistical analysis. So we're just going to look at how's one detonator performing here. So my 25 millisecond, I'm going to assume it's firing right at 25. We know that's absolutely, not going to be the case. If it does, go buy a lottery ticket if you're having a good day. But we're going to expect some difference for a representative group of detonators fired that the average is not going to be 25. But let's look at one det, say the accuracy is good. Now, how are we doing in terms of deviation? So if my deviation is 1.5% of that 25, I can see I would expect 68% of that group, of those detonators within that group, to fire within half a millisecond of that 25. And then, my worst, as I step out, 99% should fire within, if I'm looking all the way to the left there, 23.8. So we'll say 1.2 milliseconds before or after. So if I fired 100 detonators, I would expect 99 of them to fire within, 1.2 milliseconds. That's not bad because we're looking at how well electronics are performing. We're saying, well, 1 millisecond accuracy. So those 25 stacking up pretty well. However, the deviation is based on the nominal delay. So some of the potential issues start happening when you have a larger downhole delay to account for the burn front. So we can look at the 350 now. Just 1.5%, you can already see we're almost gaining 5 milliseconds before or after. So 68% within that group, let's say 100 detonators we fired, so 68 of them would fire within 5 milliseconds. That's pretty good. That's pretty good. But what happens is you step out there towards the tails of your deviation of your bell curve, you're going to see, well, you're going to have up to 15 milliseconds of difference. So there, if we go back to the, click through there. So the difference is 95 to 94, so that's 4% for the grouping. So 4% there might have up to a 15 millisecond difference from nominal. So as you get the larger in-hole delay, to account for burn fronts, and you're going to have some bigger patterns or a few different applications, you're going to be using something even bigger than the 350. You can see that deviation can get pretty big pretty quickly. So looking at a nominal 25 millisecond delay, this was work done for an electronic versus a pyrotechnic by the University of Kentucky. So for their grouping of detonators, for a group of detonators that they fired, blue represents electronics. So the nominal is 25, by the dashed line. Blue curve is the electronic performance. You can see it's slightly off. We can go over here to the right. The average firing time for the group of detonators is 25.026. And this is in milliseconds. So yeah, that's sub-millisecond accuracy for the nominal here. And then the deviation was 0.1173 milliseconds, so very tight deviation. Contrasted directly to the red representing the pyrotechnic, you can see its average firing time was off by 2.75 milliseconds, so shooting later than prescribed for its nominal delay. And then deviation numbers larger than that was observed in the electronic group. But you can see that visually too, just by the shape, or sorry, by the width here of the curve. So you can imagine here, 27.7, that's kind of your average firing time. 68, you know, that's 68% within one deviation. That's a much bigger chunk going along the x-axis there in terms of milliseconds. Here, almost everything's contained within that deviation, you know. The tails are at 25.5 and 24.5. Here, your nominal's off, and your tails are coming in 25.5, almost at 30 there, or maybe a little bit before 30. Just kind of driving home the point, they perform very differently in terms of your accuracy and the precision. So electronics here did better with accuracy. Looking specifically at electronic delay. So electronic delays are typically going to have an accuracy of plus or minus 1 millisecond of the nominal time. The accuracy is going to decrease as the nominal delay increases. I've heard this is attributed to you're requiring that capacitor to hold the energy for a greater time. So you start to lose some of the accuracy as that capacitor is required to do a longer amount of work and hold that charge before it releases to fire the fuse head. That can lead to some drops in accuracy. But for the whole programmable range, you should expect 1 millisecond, and make sure you're holding that, your distributor, your manufacturer to that. It's kind of what electronics, that's what's expected. In terms of precision, so that's accuracy. Been hitting on that a lot. So accuracy is kind of the middle of the curve there. Precision, how tight is the curve? For electronics, you should expect a deviation percentage of 0.01 to 0.02%. That's contrasted to the 1.5% of pyrotechnics, so much, much tighter. Here, I didn't even bother doing the what a precision calculation would look like on a 25 millisecond nominal delay because it's so small. I just pulled some typical in-hole delays for pyrotechnics and looked how that performed with precision in terms of for electronic detonators here. So even at 700, you can see you would expect 99% to be firing within 0.2 milliseconds of the average. And this average, even though for the example 700, the average would fall between 699 and 701. And then this would prescribe what your precision values are. Just another look here. This looks at the 25 milliseconds on the left. We already covered that. And then the 675 and 700 on the right. We have two videos. I'm just going to show one of them here. I got running a little bit behind time, it looks like. I'm going to escape out here. Bear with me as I pull over a video. So this video is going to look at the firing times between, get over here so you guys should be able to see it. It's pulling up right now. So this is going to be looking at the firing times between a grouping of detonators programmed to go off at 900 and a group of detonators to go off at 1,000. In the back, the pyrotechnics should be going off at 900, and then in the front, you'll see the electronics going off at 1,000. Sorry, I was looking off screen there, probably why it went. Okay, there we go. This will be good. So those are the actual firing times listed, and that'll be on the slide coming up. But you can see there the cap scattered are evident within the 900 millisecond range. And then the electronics, which are programmed to go off at 1,000. It's almost hard to see it visually even when it's slowed down. So I'll play that one more time here. So again, you have 900s in the back and then 1,000s in the front. You can see it there. And then here comes your electronics almost instantaneously, kind of hard with the eye there to see any difference. Transitioning back to the slideshow here. So that's just showing 900s for firing, nothing fired early, some things fired late, and then the 1000s all fired at 1000. So we talked about a lot about the accuracy and precision. Well, what's some stuff that we can do with that to drive value? So multi-priming for fragmentation. So this is the idea of putting at least, one primer in the bottom, one in the top. You can do more than that, and driving some fragmentation benefits to that. There's debating theories on whether that's due to where the shock wave's colliding, or it's just due to the power equation and releasing the energy in the hole over a short amount of time. But the fact is, if you're priming for redundancy, for safety, you could probably do that, okay, pyrotechnically. But if you're trying to drive fragmentation and you have 2 primers in the hole relying on pyrotechnic delays, probably not going to get that benefit. Because, for an example, if you consider a 30-foot column of AMPO shooting at 12,000 feet per second, that detonates in 2.5 milliseconds. So if one of your primers go off before the other, you're not going to get that collision of the wave in the middle of the hole, and you're more than likely than not potentially going to be eating up that primer just with the powder itself. So you might get some redundancy, benefit from the redundancy, to make sure that you're shooting top and bottom, or if you're having issues with cutoffs, your pyrotechnic delay in your primer, you still get that benefit. But in terms of getting the fragmentation benefit, you might not get it if you're not employing electronics. Underground perimeter and performance. Some of these can be applied to applications on the surface as well for pre-split, but the idea is you're shooting all at the same time or in groupings of holes. Accurate and precise delays are needed to make sure that those are firing together to get a neat trim line. So in tunneling, they use very much greater delays than we would be or typically used to using on the surface. So you can imagine as those delays get higher, that's 5,000 to 8,000 milliseconds. And if the deviation is based upon a percentage of the nominal, that deviation is getting up there pretty quick because you're using longer period delays to allow that muck in the middle to move out. So there have been some case studies showing the benefits of using a hybrid system where you use non-L in the middle, where the you have great enough separation between the charges that the deviation is not going to matter too much as long as things are firing in order. You're creating the void to blast to, but when you get out to the trim line, you want to have something that's firing at the same time or firing more in a zipper effect. You don't want a popcorn effect. So you can actually use a hybrid system and fire electronics there along the perimeter. Now we won't worry about the videos. Pounds per delay and PPV. So the traditional equations based on scale distance are relying upon an 8 millisecond separation. It was shown in the initial work that an 8 millisecond separation prevented waves from building up and building that PPV. You're kind of getting a cumulative effect there. Sometimes some of the case studies that you may have seen in some of the work that's come out, the 8 millisecond rule, takes a little bit, gets beat up a little bit. But kind of a thought is, you can see if historically this work was done with pyrotechnics, if you're applying these same equations using electronics, especially if you're doing site-specific development of your scale distance and your ground transmission factor, you might get better performance out of these quote-unquote old school equations because you're applying a new technology to it. Because in the past, these equations are not only have to account for all the factors that affect vibration, but your timing might have been affected as well. Because if something was quote unquote firing 8 milliseconds apart, we can see pyrotechnically, there's a high chance that it wasn't actually firing 8 milliseconds apart. Especially on your bigger patterns where it's hard to get that separation in firing time and you're firing things right at 8 milliseconds apart. That's kind of a blurred line there. So electronics might actually lead to better performance. It'd be nice to see a little bit more work in that, seeing if electronics can drive better performance out of these equations. And because I just think sometimes they get beat up a little bit. Just make sure I'm not missing anything. Sorry, I'm speeding up a little bit here at the end. This is kind of the next wave. This has been around since the 80s, but applied more and more for vibration. It's the signature hole analysis approach and looking at the frequency control. So you can fire a representative hole known as a signature hole, representative of the blasting conditions and what would be fired typically in a production pattern. Capture that vibration signal, then model it with software such that you can manipulate the frequencies, find an amenable frequency to shift it to higher frequency content or something that's maybe not producing a ringing effect on the structures nearby. And then also, besides frequency effects, you can stagger your timing delay such that you get a destructive interference effect and actually limit the PPV, if not lower it from past results. However, with all this work, you're really splitting hairs there. And if you want to stay true to the mathematical work done, you're going to have to employ electronics with this. You're probably wasting your time if you're using pyrotechnics because you're not actually going to get the firing times modeled, which is needed to get the destructive effects or to shift the frequency. Consistent burden relief and blast movement. So Brad gave some good rules of thumb, but sometimes it can be hard to follow those rules of thumb or to follow, find what exactly is working good for your cast or your fragmentation if you're constrained to the delays out of the box. So electronics are going to bring you the benefit of programmability, program to the situation needed, and then they're going to fire when they're programmed to with high accuracy with respect to that nominal delay to give you some consistent burden relief along the cast. This here is an example of a 3-row trim shot against a final wall. So in the front, they're shooting 6 milliseconds per foot. In the back, they're shooting 8 milliseconds per foot. So kind of the dual benefit here of being able to program your electronics to fire for these such specific relief values, but also then count upon the delays to fire when programmed, so you're maintaining that consistent relief. Another one here, just I think one last example in terms of muck movement. So this is kind of a very complex thing. I would hate to try to shoot this pyrotechnically and then almost kind of upon the performance pyrotechnically. They have a crest here that they're trying to shoot the contours perpendicular to prevent spillover. Because what they've done is they've filled their catch benches below this, their haul roads below this shot, and that's the only artery to the in-pit crusher to send the ore down to the mill. So they can no longer tolerate spillover. So they're shooting perpendicular because they obviously don't want to shoot straight over and spill anything that way. They don't want to flip it 180 and shoot towards the pit and get kind of a concussive, for any reaction, there's an opposite equal reaction. So they don't want to send them up towards the pit and push something back out over the crest. So they're going to try to shoot perpendicularly and shoot it into an open shovel face. But then on the inside, they're wanting to swing the contour over and pull it towards the shovel pit. So with electronics, you can kind of meet this situation here in terms of movement, and then you can have some varying milliseconds per burden relief based on what you want it to do. I believe on the outside, they were shooting a little bit slower, so 4 milliseconds per foot. And on this inside, I believe 3 milliseconds per foot. Lastly here, this was from a mine in Nevada, a silver mine. They're wanting to pull, where my mouse is, that's low grade, that's ore. They're wanting to hump these up away from the waste surrounding it. So this can be sent to the appropriate stockpile for later. The ore can be sent to the in-pit crusher, and then the waste taken to the waste dump. So something like this, you could probably get 2 sinking cuts going in a shot with non-L, but then the kind of have a weird shape. You're not just shooting 2 sinking cuts across a rectangular pattern. You have a weird shape here. And then on top of that, again, it's not just the programmability. It's counting on these things to shoot when you need them to shoot with respect to their accuracy to get that movement as designed. So just a few final thoughts here. I'm right at 49 minutes. I'll try just to go a few minutes over. Electronic initiation systems, they're going to provide increased nominal delay accuracy and precision. I don't believe that, that's really not up for debate. Just manufacturer data supports it. There's been independent studies through OSM, through universities. The precision and accuracy is there. It's what can you do with that accuracy and precision to get the bang for the buck? Because there is a price difference. It's gotten somewhat closer over the years, but you're still going to be paying more for an electronic detonator. Increases in accuracy and precision can improve safety, improve blast results, protect against litigation. I didn't touch on that one too much, but if you're blasting to the 8 millisecond rule and wanting to be the best neighbor possible, you probably take into account which delay is actually going to keep things 8 milliseconds apart. If that's kind of the equation that you're relying on to limit vibrations and be a good neighbor. And lastly, what those examples are driving at is you can decrease your total cost of operation through increased blast performance. So you're more than likely not going to get a decreased drill and blast cost using electronics. But if you look at the big picture, look at where your gains are in other areas such as fragmentation, muck profile in terms of how you lay the shot out for whatever digging unit you're using, loaders, shovels, like different muck pile configurations. But if you look at the big picture, you can justify the cost through the decreased total cost of operation. It's going to take some work. You have to be able to quantify your gains, but you can drive those gains with electronics. Just a caveat here, just because electronics are shooting more accurately and more precisely, that doesn't eliminate the need. It's not a fix-all. You can't just throw an electronic down the hole and expect that to fix anything. In some cases, you can throw an electronic down the hole and use your old non-L timing, and it's going to work great. And sometimes you can throw an electronic down the hole and use that old timing. It's actually going to exasperate a problem, because now you're shooting as designed, where before you may have not been shooting. That cap scatter may have been helping you in terms of vibration or fragmentation. Sometimes there's some crazy things that can happen. So make sure you're looking at the whole picture out there on the bench when you start to use electronics. Don't think you have to reinvent the wheel in terms of data collection or projects done or how to quantify something. A lot of us out there have our ISE memberships. If you get online, you can search the OneMind database and just find a ton of paper. A lot of people have done the heavy lifting for you already. It's a great jumping off spot for any projects you may be doing. Lastly, I'm going to run through the questions and I'll just answer them quickly. I just want to drive home on a few things. Which pyrotechnic delay is going to have the greatest deviation? It would be 700, guys. Remember, because the deviation is 1.5% of the delay. So the greater the delay, the greater the deviation. Question 2, wow, this system allows timing up to 30 seconds. I'm going to time this 2-second long blast to fire starting at 28 seconds and end at 30. Let's see what this bad boy can do. Any issues here? No, it should fire it as prescribed, but just be aware, as we said, even for electronics, the delay deviation is going to increase as you go up the nominal delay, because it's a percentage of the nominal delay, and you may lose some accuracy because you're now counting on those capacitors to hold the charge for a longer period of time. So point is, don't program longer delays than you need to, would be my advice. Can you fire electronics with car battery? Please do not try. Please don't do this. You can't. You shouldn't. Maybe I say you shouldn't be able to. That doesn't mean you should try. Because we'd hate to see something happen. You should never hook up an electronic to another manufacturing system. Only use it with the prescribed OEM equipment. Only with the approved equipment from that system. That also goes for, don't use any what's the word I'm looking for? Multimeters or anything like that. No other electronic equipment with the detonator except what came with it from the manufacturer. True or false? Well, these electronic detonators are great with safety. They require specific voltage and signal to fire. Since this is the case, blasters do not need to take additional precautions during lightning storms. In fact, the operating time saved due to this is one of the reasons so many people are using electronic detonators. That is absolutely not true. Follow all applicable rules, regulations, and procedures regarding explosives, whether electronic detonators are being used or not. Which type of delay is it important to use the same date code? So this is not referring to best inventory practices, but in terms of delay performance. So that'd be for pyrotechnic. And the thought is, if you use the same manufacturing lot, any offset accuracy will be consistent throughout the detonators used for that pattern. So you should be able to statistically maintain the separation, the firing separation time, even though if it's not firing at the average nominal time. Or sorry, its average nominal time is not firing at the nominal time. So it's trying to account for that offset accuracy. So use the same manufacturing lot if you can. A few more here. Top left is accurate and precise. top right is precise, tight grouping, but I'm not in the middle of the bullseye. The bottom left, this one gets people and can throw you for a loop. I kind of look scattered, but if I was to take the average of all 8 of these, I'd be right in the middle, but I'm not precise. And then the bottom right, I'm neither accurate nor precise. I don't have a tight grouping. The average is probably where my mouse clicker is. It's not in the middle. What's the term electronic describe an electronic detonator? It's how the delay is achieved, not how it's initiated. So our non-Ls and electrics got their name for the way that they were initiated. Electronics went a slightly different direction. It's how the delay is controlled. Lastly, electronic detonators have programmable delays. This is great. However, my blasters need to stay on top of it so I can let the salesman know which delays to have the manufacturers and the guys in the factory program them. So that way I'm not getting detonators on site with the wrong delays put in the memory. False, the user can program the specific delays, and this flexibility is a benefit. So we ran through the questions there pretty quickly, guys. No, sorry guys, Rio, that I went over there, but if we still have time for questions, or if we don't, I can take questions offline and get back to you through email.
I don't have any questions for you. Just a different perspective here. Some of the complexity of some of those shots you're showing, we just don't see that in the Powder River Basin. So we're more about volume and moving lots of it.
No, that's a good point. I think in the Powder River Basin, where you're going to see electronics used pretty consistently would be in the cast. And without referencing a specific mine here, this was a case study where I think the cast, they showed a 6% improvement in cast by using electronics to tweak the timing there. So they were able to reduce those yards and increase the cast by 6%. So I think if you guys are going to be seeing electronics, you're right. It's typically going to be in the cast, not some more of those complex areas. But we're seeing a lot of blasters. You know, we have seen blasters migrate out of Wyoming in response to the market. So it's not a bad idea to have some of these ideas in your head.
Vince, we did have one question from Tyler Smith. Are there any manuals available for the digital shooting?
In terms of, you know, timing schemes, or is this a question in terms of manuals for a specific manufacturer?
Tyler, we can probably just unmute your mic, and that way you can see if you can talk with here directly. Looks like you are self-muted. Well, looks like we can't get Tyler. Tyler, if he says DigiShot.
Yeah, so I'm seeing an email there, tsmith6548@gmail. I'm not sure what site he's working at, but yeah, for DigiShot Plus, you know, I can communicate with you directly, Tyler, and get you what you need. But there's plenty of manuals and PowerPoints, you know, so just ask your manufacturer. They're typically going to have a big manual, you know, 90 to 100 pages, but then they also typically have cheat sheets and PowerPoints that can help you out there as well. And a lot of people move into different multimedia things too, such as videos.
Hey, Rio, did we want to take a break, or did we want to just keep on moving?
Let's just keep going. I did have, there was a question about who to contact for if you're having trouble getting hours. And just a reminder, this is just for Wyoming. I don't control any other states. But you would, I wouldn't mind just showing my contact information again, if you don't mind.
Yeah.
Okay. All right, there is my contact information. My phone number is 307-675-5612, and then my email address above that as well. So yeah, if you're having issues, please give me a call or shoot me an email. We can talk about that, because we did have to cancel several classes in this past summer. So,
Great.
all right.
Well, all right, we'll move forward. Baron, do we got you?
I am here. I'm just getting ready to share a screen here, if I could.
Okay.
Let's see.
All right, be right there, Baron. Bear with me. We did have it there briefly there, Baron.
Not anymore.
No, not anymore. There it is right there. You just need to maximize it now. So we have your
screen there. Is good.
Hey,
so
Baron, just hit escape real quick. Yeah, if you would just hit escape real quick, when you hit that button, hit the one down just to the left of the display one. Just hit, yeah, in slow show, slideshow. And then that one to the, go over to the right there, that, nope, other just to the left. It should say, go one over to the left, other left.
Notes, they're normal.
Nope, go to the right, one more, that one. Hit that button.
Rating view.
There you go.
That good?
Yep.
we're good to go.
All right. Good. All right. Thank you very much. Everybody good?
We are.
Not letting me advance. Yeah, it's not letting me advance that. There it goes. All right. Rio, I didn't know if you had anything you wanted to touch base with, or if we just wanted to jump in here.
Yeah, and this is a presentation. Yeah, this is a presentation I requested on Blaster's personal liability. I had an incident this past year. Blaster shot. It was questionable. It wasn't completely horrible decision. Ended up having to put the Blaster on probation. And at the mind just didn't quite understand how the Blaster can be held personally accountable. So I kind of got the feeling that overall that it wasn't really quite understood that blasters could in fact be held personally liable. So that's why I requested this.
Okay, thank you. So we'll just touch on a couple of points here on liability and blasting incidents, just your personal actions that you can take, what you should be, some things you should be looking at. I'll share a story here, an example of an incident and how that was handled, just as an example to get you thinking. We'll talk a little bit about misfires and misfire avoidance, but won't get into the weeds too much there. And there's a few slides there at the end, just touching base on the Wyoming blasting regulations. So first, starting out here, really the best website to go to if you did have questions around Wyoming, your blaster's license, or just wanted to understand or refresh your memory on the procedures there, is just the DEQ.wyoming.gov site, and you can type that in. I found it pretty easy looking at the blasting regulations, and actually found it very helpful just to kind of glance through those. So I didn't want to get too much into that, but the one example here is it's very important that you understand what the regulations are, whether you're in Wyoming or whether you're in another state blasting, you know, and in Utah, we only have a requirement for surface coal. You don't have to have a license for quarry or construction. So again, but still understanding what is expected of you and maybe having a dialogue with your local officials is really not a bad idea. Personal liability does equal blasting activity, right? Blasting is considered a hazardous occupation, and in turn, when you do blasting, we're expected to know what's required from a regulation standpoint and a procedural standpoint, right? Because we know more than the average citizen, hence that makes us kind of an expert. So you're considered to be an expert in your field, meaning you know and follow. Didn't know is really not a good answer. And you know, you can call your local authority and ask them a question before you start, or even phrase it with hypothetically, I ran into a situation and what if I would have done this, right? So it doesn't hurt just to have some different ideas out there on how you might tackle a particular situation. Understanding, you know, that if you are liable for damage created or caused by a blasting activity, the claimant only has to prove that you or that the activity more than likely caused the damage. Not required to prove the blaster did something wrong. Not required to present an expert opinion. Burden of proof basically is on you and your company, right? That you kind of are guilty until you prove yourself innocent. You cannot prevent all claims, but you need to have your documentation completed and accurate, right, to give yourself the best chance. So when I say that, waiting for a week to complete your blast report does not really give you the best chance to succeed. You need to complete your blast report and your documentation as soon as practical, so that the information is fresh and that it's accurate. Because being up on a stand and having the plaintiff's attorney discredit you because you know you can't recall certain facts because you left them off the blast report doesn't side well with you on your side. Blaster is the person in charge of the blast event, right? You have the authority based on MSHA, based on set regulations, to conduct what goes on in that blast. So it's more than a title and a t-shirt, right? There's a lot of responsibility. MSHA needs you to be able to explain the products that you're using. So if they come up on site and you're using a dual detonator, dual delay detonator, or an electronic, right? You have to have an idea of, you know, explaining what that means. And that's part of what this training is about, to provide that knowledge share. People on the pattern need to be confident. They need to be cleared. So they need to become on by your authority. And that includes someone like myself. You know, they need to ask permission and they need to be contributing. So just having people stand around and talking about the football game last night or something like that is not contributing. And you have the right to walk over and just ask them if they could just take their conversation outside of the pattern so that you guys could not have to worry about them or maneuver around them. Communication's critical. Just because you have a hold harmless agreement doesn't release you from an investigation or a court of law. It is a documentation that's useful. But keep that in mind, it doesn't release you just because they've signed it. Customers signed a release agreement. It does not fully release you, especially if it gets to a court of law. Blaster is a person in charge, so they have to design, they have to understand the stemming, how the delays work, the workplace inspections, right? So you have to inspect the work area before you allow people into that site or before you designate it as a blasting site. And then you have to ensure that you've got good seismograph monitoring and that it's compliant. If you've got scale distance calculations, you've got to do those to ensure that you're in compliance. And then communication to the blast crew to ensure that all the holes are safely loaded, that everything is communicated, that people understand what their jobs are and how important they are. And if there's an issue that they need to bring that to someone's attention, right? Not after the fact, but at the time. And then really the last point, pointing the finger in another direction is not acceptable. The burden is on you as a blaster, and that's kind of what we talked about. It's just more than a title and a t-shirt. You really have to understand that your employer trusts you, that you're going to work safely and you're going to work honestly and provide good results. So liability with blasting incidents. Understanding what is required for a blasting permit and local regulations. Again, saying that I didn't know is really not acceptable. It's your job to go on and ask and read the documents and understand how they apply to your particular situation. Defining what's considered to be as a near miss event or an incident. So as a blaster, you get to establish, and we'll look at a slide here in a minute, what that blast site is, what the safety zone is, where people and equipment can be, and then where you're going to safely fire it or initiate the blast. So safety protocol for stopping, assessing, and communicating is critical, and everybody needs to understand that that's on your crew. Documentation in case there's an incident, whether that's reviewed by Wyoming DEQ or a local agency. It's very important. When I did a lot of work down in Florida, it was very important because we had a separate agency that managed construction blasting. And so I just took it upon myself to build a rapport with the individual that worked for the city or for the county, so that I understood what the regulations were. And then if we had an incident, just was able to provide him with the information in order for him to do his investigation. So be a part of the solution. Uncontrolled blast events. When we're looking at blasting definitions, we have to plan and compare with what actually occurs, right? That's how we improve ourselves, and that's how we learn. So, sometimes and many times things don't go as expected. It happens to me quite often where I get out there, a bulk truck doesn't perform. The pattern wasn't drilled quite the way it was supposed to be. Some holes, some material fell off the crest, and so the driller moved the first couple holes back. Whatever that situation is, we've got to learn from it and adjust, because we want to make sure that we understand what our fly rock area is. And I just have this as a kind of a definition, asking yourselves, what is that designated area going to look like, right? I just don't have the whole permit boundary, because I need a margin of safety, and I can't move equipment off the permit boundary. So asking yourself what that is, whether it's half the distance to a permit area, whether it's, for an example, 300 feet in a quarry. And maybe we need to ask ourselves what that looks like to the sides and to the front and to the rear of the blast. Then we need to look at misfires, and we really need to understand what caused those and how we can prevent those from happening in the future. So unexpected blast events really can put us in a situation where we're out of our comfort zone and we're out of our expertise, such as trying to do a sinking or a lift blast, right? Or we've got some tight digging conditions. We want to make sure that we understand what caused those and how we can learn from them. So I used to track a lot of the blasting incidents across the country as far as number of blasts, and I know we're on mute, so I'll just kind of move through this, but I used to ask what day of the week, right? And so ask yourself, what day of the week do you think misfires and fly rack incidents typically would occur? And in this case here, I tracked them for a year at these particular sites, and we can see that Monday and Friday were pretty high days. And that makes sense, right? Because Monday we're trying to gear up, we're trying to get our head back in the game. Friday we're trying to think about what's going to happen for the weekend. We got a football game or an event to go to Friday night. We've got some weekend activities with the family. And so our mind gets distracted. We also get distracted by conversations with our fellow employees, our colleagues out there. So keep that in mind. Sometimes Monday morning, having a good tailgate meeting, get people's focus back in the game is a good thing. And same with on Thursday and Friday. In fact, it's every day of the week, right? It's time to focus and to pay attention to the details. October and November were the highest months throughout the year. Maybe you could attribute it to sporting events, maybe hunting and fishing. I'm not really clear on what that is, but October and November tend to be the highest months throughout the year in which we have an incident, right? And when we talk about incidents, that's the liability on the blaster. So if we have a misfire event, you know, it doesn't matter if you told me to go check them and I didn't check them. If you're the blaster in charge, the customer expects that you will check them, or that you will ensure that the person that you asked to check them is competent, qualified, and actually does that. So keep that in mind. When we define a blast area or a blast event, we as a blaster get to decide what that blast site looks like, right? So we get to have a berm around the blast site. We get to put our signs and our cones out. We get to go down in front, determine if there's equipment that needs to be moved out of the way, or if they can finish mucking this particular end of the blast while it's being drilled out. So we get to define what that is. And then we need to look at kind of an area that's past where we're actually working, where the material is going to be moved into. And we call that kind of the blast area in this particular example. So we know when we do the blast event, we're going to have material that's going to move forward, maybe to the left and to the right, maybe even a little bit to the back, depending on the rock material and how we load that. So we get to define what that perimeter is as a blast area. And then it's our responsibility to create a safety buffer. And that's a buffer that says, you know what? I think material is going to go 300 feet. I'm going to give myself another 200 feet or another 300 feet, whatever that may be. We get to define that based on the knowledge we have on how the pattern was drilled, how it was laid out, how it was loaded, how the geology is, how the rock typically moves. We get to define that based on the knowledge that we have and the experience we have there. And then we've got our safety zone, and that's where we can have equipment. We can have people, and we can have things that are in that safety zone that we don't expect to have any issues with it, that everybody can return to work once the blast event is completed. Oops, sorry, I don't know how we got back to there, so I'm sorry. So really, I don't want to get too much into this on the blast area, but that's just where we expect flying material to occur, and so I've kind of covered all this. So potential for property damage. We need to conduct a pre-blast assessment looking for potential hazards, right? I'm really amazed when I chat with some blasters that they never ever took the time that morning to drive down in front of the face into the pit to see if anything changed, right? Did material fall out of the face at night? Is there less burden there than when we designed it? Did someone leave a piece of equipment down there, like a pump or something like that, or a light plant? And, you know, does it need to be moved? So it's really our job to kind of do an assessment of the area, look for equipment, and then understanding your distance to your nearest structures, right? Looking at the map on the wall in the mine office or on your aerial map and understanding what those distances are before we even start loading. We need to understand the potential for property damage, right? This is really about personal liability. If there's property damage, and you're the blaster in charge, they're the ones that are going to be talking to you. It doesn't matter if somebody else was at fault or not. You're the person they're going to be talking to. So if there's an issue, tell your people to don't commence loading, right? Stop and let's have a conversation and figure out what a better solution is. There's a hole that got plugged off or something like that, okay? Record your blast events. I know we all have access to our handheld cameras on our phones, but really trying to hold your camera and record in your hand, initiate a blast and get a quality video, especially if there's an incident, because your hand travels where your eyes are going, so you're going to miss something. That's really not the best solution. I know the picture here of this guy using a video recorder, we would all say is a little bit outdated, but in reality, the odds of him capturing something on that tripod once he's hit the record and then stepping away from it are actually pretty good. So maybe another solution is using a drone when possible, right? And then you've got a different vantage point, but record the blast event from start to finish. Very important, especially if you have fumes that are coming off of the blast. So if you've had ANFO that's gotten wet, or you've had product that's slept in the ground longer than expected, and you get some post-blast fumes, it's very important that you capture that and track it, right? Because if it leaves or crosses over the mine permit boundary, now we're getting into, again, a discussion about personal liability, right? And you can't have that. Ensure documentation is complete and accurate. We touched on that, making sure that your documents are completed throughout the blast. So if you have to document how each hole is loaded, using your drill logs to line that up with, so that you know where the holes are that you're loading and what ones you had to short load or which ones were overloaded. You want to make sure that that stuff is documented. Post-blast inspection. Do not sound an all clear until you have conducted a post-blast inspection. It's really important that you take a drive once the smoke and the dust have cleared, that you take a drive down there and look at the blast and really ask yourself, did everything go, right? Just because it all moved away from the wall doesn't mean everything initiated. You really have to look at the muck pile and ask yourself, did it all initiate, and does it look like it's supposed to look? And then you can check for unsafe ground and high wall conditions. So if you run into some unsafe ground or an area that's unstable, then you can report that back to the pit foreman, right? And then they can come up with a solution on how to best to handle that. Bring a track hoe up or something like that and knock it down. So I'm going to share a fly rack incident with you. Put kind of what the saying, sharing is caring. I just want us to kind of learn from this example a little bit. We can see this quarry. You've got blast tower in the middle part of the quarry. So there's 5 benches there. And you had a loader and a haul truck located at the very bottom, moving some material around. And then you had a drill and a compressor right there, working right above where the loader and the haul truck were located. And the view from the video camera location is where we're kind of looking into the pit from this location. So they did have a video on it, and that's the right thing to do, right? So here's an example of, there's the blast right below us, the muck pile. So that'd be the top of the blast, right? So you can see it's pretty hard to see down into that pit. And again, if you don't take a drive down, see what's down there, how would you know that there's a drill and a compressor sitting there? Here's the haul truck and the loader working on the bottom bench. Here's the hole that the rock traveled through the windshield of the loader, hit the operator's seat. We can see from the cross section of what blew out, that was probably from one hole. So was the hole overloaded? Was there a seam there? You know, again, things like that you would want to document and look at before you ever started loading. And driving down and looking in front of the face might give you some clarity to that. Looking at the drill logs and lining them up might give you some clarity to that, where you could make an adjustment before you started loading holes. So lessons learned. Pit foreman was rather inexperienced. The only blasting that this person was exposed to was kind of picture perfect blasts, right? So all the other blasts that they've been doing for months, there was no issues with them at all. But this particular one had a blowout. So the pit foreman felt comfortable that blast only moved about 100 feet. So we left personnel at a distance of 400 feet. Blaster had no view of the pit or the lower benches. So when the blaster asked the foreman if everyone was clear, maybe the question should have been, is everyone out of the pit? And so some of the incident liabilities that needed to be asked of this is, why was everyone complacent with leaving equipment and personnel in front of a blast? Who's responsible for clearing the pit? The blaster is responsible for clearing the pit. Now he can have the foreman do that, and the foreman can drive through the pit and provide that all clear, but the blaster is ultimately responsible. Who's responsible for communication during the blasting process? MSHA says that it's the joint responsibility of the blaster and the pit foreman. The blaster cannot escape their responsibility, even if they are told it's all clear to initiate the blast event. So corrective actions and avoidance. The pit, and this is just an example of this particular operation. I'm not suggesting that you do this at your operation. I'm just sharing kind of what came out of this. So we've got engineering solutions and we've got procedural solutions. So the pit will be entirely evacuated regardless of where the blast event's located, right? A good procedural solution. The quarry erected a gate at the entrance to the pit that must be locked after clearing the pit. And the blasting contractor now uses remote firing machines so that they can have a view of the pit. So again, just some examples of what they did to ensure that something like that would never happen again. Another example, incident, one way it should be handled. A blaster at a coal pit told the mine foreman that equipment would have to be moved before a blast. Foreman moved it back about 50 feet, but it was still 300 feet from the blast and 150 feet down below. There was no catch bench between the high wall and the equipment. Blaster asked the foreman to move the equipment out of the pit, and the foreman replied that the blast shouldn't go that far. Blaster told the foreman that they could not put off the blast unless there was a hold harmless agreement signed. Mine foreman signed the hold harmless agreement because he didn't want to take the time to move the tracos out of the pit. Here's the blast event, and there's the two tracos. While liability cannot be fully transferred, it does help to show the importance of addressing a potential situation. So, you know, sometimes using a hold harmless agreement or having that discussion with a pit foreman helps them to understand the importance of the situation and how you feel about it, right? There's the blast site behind the two tracos, and there was damage to both tracos. One had a glass and interior damage to the cab. The other one had major damage to the body and the radiator. But there was a hold harmless agreement signed. So from operator standpoint, from a quarry or a mine standpoint, the mine did have to pay for that. So let me ask you this. If this was your pit foreman and they signed that and you had, you know, you could add it up how many tens of thousands of dollars it was, you know, your job might be at risk here. So you really have to keep that in mind when you're talking about personal liability. I only have one of these slides up here. It's just talking about it. They were put out by the U.S. Bureau of Mines, and you can go locate it. There's one for limestone, there's one for sandstone, and there's one for shale that the U.S. Bureau of Mines did. I put it up here just as a reference. I like it. I like these three graphs for limestone, sandstone, and shale because it provides just a good reference of how far material will typically travel. So right in the middle is the 6-inch hole, 6-inch diameter. So for example, if you had 20 feet of burden, you could just calculate this up, come on over here, and you could expect that material is going to travel about 80 feet forward in that direction. And so it kind of gives you, maybe helps you with, you know, understanding how far material is going to travel, and maybe even helps you with your conversation with moving equipment out of the way. Fly wreck liability. It's the most serious potential hazard in blasting. It's the single greatest cause of injury and property damage. We must constantly reassess the safety zone to ensure that fly wreck incidents do not occur. And failure to secure an adequate safety zone is the primary cause for fly wreck damage and fatalities. Any equipment left inside the blast area must be considered at risk. So perform a job safety risk analysis or a risk assessment, whatever you'd like to call it, as part of your pre-blast tailgate. And many of our fly wreck incidents are due to modifications in the blast design, right? So here's how we laid it out, here's how we designed it, but when we get there, that's not the way it was actually drilled out. There was a modification. Neglecting to get others involved in finding a solution. Don't be afraid to pick up a phone and make a call to one of your colleagues maybe that has experience, or even someone else, maybe it's outside of your company, and just ask them, you know, in that situation that they had, how did they handle it? And do they have any ideas that you maybe haven't considered? And especially if you got various types of blasting that are not typical. So I've been around a lot of blasters where they can kind of go and shoot the same quarry every day and shoot the same formation every day. But all of a sudden when the quarry asks them to put a French drain in or do some pre-stripping or take down a little bit of the, you know, can you shoot this old concrete silo down or this footer out? that's where it gets them into trouble, because it's something that takes them out of their normal routine. Common causes of fly rock. Common causes insufficient burden, geology such as seams and voids, insufficient stemming, refiring of misfires, overloaded holes. So the picture there is a hole that I loaded. We were loading some blended gas emulsion products, so it was a 70% emulsion that was chemically sensitized, and then it had some 30% amphil in it. And it came up, it rose 4 feet. We stopped. I was talking to the blaster. He was bobbing the hole. He wasn't paying attention. The truck operator wasn't paying attention. I was distracting the blaster, and we loaded it right to the collar. So the only thing you can do is to call the pit foreman and have a discussion of what happened, right? It was on the face. We had electronic initiation in the hole. We were able to time that particular hole at the end of the blast. So at least we were able to fire the primers so they're not in the muck pile. But they didn't get any performance out of that particular blast. So it happened that easy, where you're just having a conversation and someone's not paying attention. Or in our case, 3 people weren't paying attention, and we end up with a situation like that. Secondary blasting. That's another one where all of a sudden you're asked to shoot a couple boulders, and the only way that they can do it is they drilled it with their production drill, and those are maybe 9-inch holes or something to that effect, right? And then how do you load those correctly? And how do you initiate them? And how do you ensure that you don't have material that's flying all over the place, because you just really want to crack them into 2 or 3 pieces. Stemming liability. Stemming the holes is really important. Be careful to avoid bridging. Monitor the volume during stemming to determine if bridging has taken place. If bridging occurs, let the blaster know, and so they can take some steps to correct the situation. The first blast I was ever on, they gave me a shovel and they told me to stem holes, and they walked away, and they started loading holes at the other end of the pattern. And it took us two and a half days to load this blast, right? So they're drilling, we're loading, we're following the drill, and I'm the poor guy in the back, trailing behind, trying to stem holes, no stemming material, some drill cuttings. No one ever told me how important my job was, or really what I was supposed to be doing. And so anything that I could get in the hole is what I tried to put in the hole. So once I couldn't find any more drill cuttings, then I looked for little rocks to try to put in the hole. And then after a while, if it was a little bit bigger rock and it happened to bridge it off, just made my life easier for that particular hole. And the reason why I share that with you is because we did have a fly rock incident out of that particular blast, right? And they hit a building, they hit some power lines. And the reason for sharing that is because really nobody ever told me and took the time to tell me how important my job was. And they didn't provide the right material for me to stem the hole. They just kind of walked away and forgot about it. And so it's really important that every member of your crew understand what their roles are and how important they are. Making sure that you've got the right stemming material there, right size. Here's a couple of rules of thumb: 1/8 times the borehole diameter, or 3/8 inch minus for construction jobs. Stemming height, you may have your own formula there, but that can give you an idea. 0.7 to 1 times the burden for stemming height. And then construction, I usually use 20 times the hole diameter for a stemming height for competent ground. Okay, misfire liability. First steps when we have a misfire is we have to wait. So if we suspect that we have a misfire, right, the blast didn't go off, something didn't feel right, the ground underneath our feet didn't shake like it normally does, something triggers our mental capacity that we had a misfire, we need to wait, right? So 15 minutes for electric and non-electric, 30 minutes for electronics and cap and fuse. Maintain blast area security. Notify pit operations manager and the job site manager Every misfire needs to be handled uniquely to that particular situation, right? So this is really where you don't want to have an incident turn into an accident. You want to get some other people involved, have some discussions, come up with some solutions. And then even considering contacting MSHA, right? Making sure that you're the one that contacts them and gives them information. Even if it's just one hole and you can safely refire it. Or to contact your local agency. It doesn't hurt to at least let them know. Trying to determine the cause of the misfire is important. Diagram the blast of the misfired holes. Examine the surface detonators and determine if you can reuse them or if they just all need to be replaced. Measuring the face burden. Never refire a blast without supervisor approval. So you've got to make a phone call and get some people involved and make sure that they understand the situation. And extend out the blast area, right? Now you've got material that's been broken up. So you want to increase your safety zone and make sure that you've got people and equipment further back. And then you can wash out holes to reduce the column load or to remove primers if required, if you're able to do that. And you may need additional material on the blast or at the toe to prevent fly rock. So that could be another option. If you can't get things washed out, maybe you bring more material in and put it on the hole or in front of the hole. It's unsafe to refire, and if it's unsafe to fire and you can't flush it out, leave unburdened holes disconnected, and then deal with them, mark them, and find the primers afterwards. This is a last resort, but drill holes behind misfired holes and shoot as a separate blast. Benchmark the location of unfired holes. This will greatly aid in the excavation of undetonated explosives after the refiring. It seems to be common for blasters to want to refire misfire as quickly as possible. It's because we're embarrassed, right? We screwed up and we really just want the problem to go away. And that's where it's really important not to let an incident like that turn into an accident. Never rush into having an accident. Don't rush into refiring them. Here's our one example of checking, right? It's very easy when we walk this pattern to see that everything is connected. We've got the oranges in first, the yellows in second. In this case here, they actually used some electrical tape and they taped them up. And so you can see when you walk past this, even if you're trying to talk to me about last night's school event, I can see that everything is neat, connected, pointed in the right direction, and it's easy for me to check that. Again, maybe there's another solution that you've come up with. Maybe there's some spray paint, or it's the way you cover them by hand, or however that may be. But make sure that you've got a procedure that everyone understands and they can follow. Keys to good blast. A good blast is attention to all the details, right? Good blast design, get accurate measurements. Know your distances to the nearest structure. Drilling accuracy. Make sure that you communicate with the drillers. They're a part of your team, right? Engage with them. Don't just ignore them while they're up there by themselves drilling, and then once they leave, go check out to see what they've done. Go engage with them and communicate with them. Carefully loading the blast event, right? Using the best explosive products available, good stemming material and the right stem heights, and then appropriate delay pattern and timing. And then understanding and establishing that blast site security. Communication at the time of blast clearing and initiation. Minimizing post-blast fume emissions, especially if they could leave the permit boundary. It's a very important fact right there. You're liable if the blast emissions, dust, and or post-blast fumes travel over the permit boundary and into a town, neighborhood, or onto someone else's property. It's a personal liability. So you need to keep that in mind when you're looking at all the other things that are above that as far as using the best products to get the job done, the right delay timing, the right stemming. That's part of your personal responsibility. Make sure all those things happen so that you can minimize or eliminate a chance of fumes going onto someone else's property or into a town. So personal liability questions, blasters assumptions. When filling in a blast report, if you don't have the data, then leave the question blank. No, I would put a dashed line. I'd put NA for non-applicable. but I would put something there just to let people know that that particular event, or if you don't know, then you can leave it blank and then ask and find out what that detail is and fill it out. But you need to do that pretty quickly. Have a hold harmless agreement signed by the customer. So it is their problem should a rock hit their equipment. Yeah, it probably is theirs, but if it goes to a court of law, it's not going to release you from liability, right? So depending on how that customer handles it. And it doesn't give you the right to then ignore that you're going to be hitting something. So you've still got to do everything you can to eliminate that potential fly rock event from hitting equipment. Not exactly sure the regulations for this particular situation, but since we are a long way from the homes, it shouldn't be an issue. No, you have to understand what the regulations are. Print them out, read them, and make sure your crew understands what the regulations are as well. One seismograph is charged, so we will place it at the permit boundary rather than the closest residence. Well, that might be the case. I don't know how it's written for that particular project, but most likely you need to place it at the nearest residence. But again, you'll have to understand how that particular blasting permit is written. Only a small piece of coal traveled on the topsoil area. No need to worry about one piece. No, that's incorrect. You have to worry about one piece. In fact, I had an incident with putting coal when I was a younger blaster up on the topsoil. And then the next day, people are out there walking the topsoil looking for the coal that I'd put up there and then picking it up. And it was an incident that was discussed with the regulators, right? Because that violated the blasting permit, was having coal up on the topsoil. So again, it's something that has to be considered. Don't have a warning siren, but the pickup truck horn will work just fine to warn others of the blast. It's not acceptable. You can't hear it. You've got to be able to hear it outside of your safety zone into the zone where you're going to be initiating a blast, right? So everybody's got to hear that particular horn siren, that warning siren, I should say, within that area. So a pickup truck typically doesn't have a loud enough horn to do that. So you've got to plan in order to get a siren or some kind of audible radio communication that lets people know that you're going to be blasting. Just a couple of slides on Wyoming DEQ regulations. These are found here that I looked at, and I really just wanted to share a couple of points from a liability standpoint with everybody. And this is right out of the regulations. Following written notice and opportunity for hearing, the blaster certification will be revoked or suspended upon finding of noncompliance of any blast-related order of Land Quality Division or state inspector of the mines. Unlawful use in the workplace or current addiction to alcohol, narcotics, or other dangerous drugs, violation of any provision of the state or federal explosives laws or regulations, and providing false information or misrepresentation to obtain certification. If advance notice and opportunity for a hearing cannot be provided, an opportunity for a hearing shall be provided as soon as practical following the suspension or revocation of your license. Upon notice of revocation, the blaster shall immediately surrender to the Land Quality Division the revoked certificate. Certificates will be protected from loss, theft, or unauthorized duplication, and any such occurrence shall be reported to the Land Quality Division immediately. Certificates shall not be assigned or transferred. The blaster shall not delegate their responsibilities to any individual who is not a certified blaster. So again, those are just some things I wanted to point out. I had my Wyoming blasting license for about 14 years for surface coal. I've let that lapse just because I don't really get, I'm not the responsible blaster like I used to be. So I don't have to do that. And I held on to it for a while, but in reviewing the regulations, I thought that these were important, right? You know, you can't transfer misrepresentation to obtain a certificate, right? So you can't falsify the training. I can't say that I've given you the training when I didn't. You can't say that you accepted training that actually never occurred. And I think that's where it's important that we're all here today and trying to have engagement and learn and get hours that are part of making sure that we renew and maintain our blasting license. So that's all I have. If anybody has any questions, I'll be glad to help answer. And unlike Vince, I'm 3 minutes behind, so I'm doing good.
Baron, it does look like we got one question through the system. Is there a possibility to obtain a copy of the PowerPoint? Yeah, we can probably get that uploaded. If you'd like to send that over to me, Baron, and I can upload that to everyone. Is there any other questions?
Yeah, this is Rio. So for the blast sirens for coal regulation, needs to be audible. For the sirens, need to be audible within a half mile. And then
Thank you.
yeah. And then just a reminder too, fly rock incidents that go off site, very high potential of blaster suspension. Again, most of our fly rock incidents in Wyoming are fly rock on topsoil, or that's not necessarily a good thing, but that's more of an environmental thing. So most of our fly rock incidents do not leave the site. So, but thank you, Baron.
Are there any other questions from the group?
So how do I, on your PDF of this, how do I get that uploaded here? Is there a way to do that?
You can actually send that to me, Baron, and then I'll get that uploaded.
Okay, okay.
I guess with that, we're going to conclude this presentation and this webinar. Once again, you can always reach us through the system as well if you have additional questions or comments. And once again, thank you all for attending.
All right, thank you, everybody.